Hello there, and welcome to Sleepy Cosmic Lens, where curiosity gets cozy and science takes the scenic route to slumber. Have you ever had the unsettling feeling that the universe is bigger than it lets on? Not just bigger in the sense of more galaxies or more space, but bigger in a way that challenges the very idea of what space is. It's a quiet thought, one that whispers in the back of your mind when you're staring at the ceiling in the dark. You know the dimensions you can see, the length, the width, the height of the room. They're familiar, comfortable, and complete. But what if they're not the whole story? What if your familiar room is just one room in a cosmic house with a floor you cannot see, a direction you cannot point to, a secret passage built into the very fabric of the air you breathe? Tonight, we're going to rest our minds beside one of the strangest ideas in modern physics: the possibility that the universe may be hiding a fifth dimension. Not hiding it like a magician with a coin behind the ear, although physics does sometimes have that same slightly suspicious charm, but hiding it in a deeper sense. It may be folded too tightly for us to notice, stretched beyond the reach of our senses, or woven into reality in a way that affects everything while staying quietly out of sight. We'll journey through the familiar space of our everyday lives, the world of left and right, up and down, forward and back, and gently unravel why it might not be the whole picture. We'll explore Einstein's revolutionary idea that space and time are not a stage but a fabric that can bend and stretch. We'll imagine the strange, elegant dream of a curled-up dimension hidden like a tiny, invisible loop at every point in the universe. We'll even consider the possibility that our entire cosmos is just a vast cosmic sheet, a brain, floating in a higher dimensional space. And we'll ask the big questions. Could a hidden dimension explain why gravity is so weak? Could it be the key to unlocking the deepest mysteries of the cosmos? We'll navigate these ideas with care, allowing ourselves to wonder without needing to grasp the ungraspable completely. We move through the world with great confidence most of the time. We walk forward and backward. We turn left and right. We climb up and down stairs, sometimes with grace, sometimes with the dignity of someone who forgot there was one more step. And these are the directions we know. They feel obvious because our bodies are built for them. Our eyes judge distance. Our hands reach through space. Our inner ear tells us when we are leaning, falling, or spinning. To us, the world has height, width, and depth, and that seems like the end of the matter. A room is a room. A road is a road. A cup of tea sits where it sits, usually just far enough away that you have to shift under the blanket to reach it. But physics has a habit of asking the quiet question no one else notices. What if the directions we can move in are not all the directions that exist? What if reality is larger than our senses can report? What if our universe is not the whole building but only one floor of it, and somewhere beyond the walls, above the ceiling, or through a direction we cannot point toward, there is more space than we have ever touched? Before we wander into that strange possibility, I would love to know where in the world you are listening from tonight, and what does the space around you look like right now? Are you in a quiet bedroom, a dim living room, a parked car under streetlights, or somewhere with a window open to the night air? It feels fitting to ask because a video about hidden dimensions begins with the simple space we already know. Your room may seem ordinary, but even there, every corner, every shadow, every small distance between you and the nearest wall is part of the great puzzle. We're always inside space, always surrounded by it, and yet we may understand less of it than we think. If you find this gentle journey soothing, intriguing, or just a calm way to let the day loosen its grip, I would be truly grateful if you gave the video a like and maybe subscribed. It helps this quiet little corner of science reach other curious minds who might also need a peaceful place to land. And as always, I hope the ideas are interesting enough to keep you company, but not so loud that they keep you awake. If sleep arrives before the end, that is perfectly allowed. The fifth dimension will not be offended. It has waited this long without introducing itself properly, so it can wait a little longer. So settle in. Let your shoulders soften and allow your thoughts to drift into the shape of space itself. Tonight, we're not beginning with rockets, telescopes, or glowing galaxies. We're beginning with something much closer. We're beginning with the simple fact that the universe gives us directions. A bird can fly upward. A stone can fall downward. A person can walk across a field. Light can cross a room. Everything we know seems to happen inside this great invisible container called space. It does not have color or smell. You cannot scoop it into a jar. You cannot place it on a table and say, there, that is space. And yet, without it, no table could stand, no star could shine, and no one could lose their keys in exactly the same place they were looking 5 minutes ago. For a long time, space seemed like the most ordinary thing in the world. It was the stage where the universe happened. Objects moved through it. Planets traveled around the sun through it. Apples fell through it. People argued, built cities, crossed oceans, and eventually invented alarm clocks inside it, which was perhaps a mixed achievement. Space was the background. It was just there. But as science grew sharper, that simple picture began to change. Space was not just emptiness, it had structure. It could stretch, it could bend, it could behave in ways that no human instinct was prepared for. And once physicists realized that space was not as simple as it looked, a much stranger question became possible. If space can bend, if space can expand, if space can be shaped by mass and energy, then why assume it has only the directions we happen to notice? That question is the doorway into the idea of extra dimensions. A fifth dimension is not simply another place far away like a distant planet waiting beyond a telescope. It is not somewhere you could travel by pointing a spaceship north, south, east, west, up or down. If it exists, it would be another kind of direction altogether. A direction not available to our daily movement. A direction that may be real in the mathematics of nature, but hidden from the direct experience of creatures like us. At first, that sounds almost impossible. How can there be a direction we cannot point to? A direction we cannot see? A direction we cannot move through? But this is where the imagination becomes useful as long as we keep it calm and careful. Imagine a tiny insect living on the surface of a sheet of paper. To that insect, the world might seem to have only two directions. It can move forward and backward across the page. It can move left and right across the page. If it is small enough, and if it has no way to lift itself from the surface, the idea of up and down might not be part of its ordinary reality. You could hover just above it with a finger, and from its point of view, your finger would not approach from a known direction. It would simply appear, touching its universe from outside the directions it understands. To the insect, it might look like magic. To you, it is only height. Now, of course, we're not insects on paper, and the universe is not quite that simple, but the example helps loosen the grip of habit. It shows how a dimension can be real, even if a creature is not built to experience it directly. A being trapped on a surface might never see the full room around it. It might think the surface is all there is, and perhaps in some deeper way we may be like that. Not because we are foolish, but because every creature knows the universe through the instruments it has been given. A bat senses with sound in ways we do not. A bee sees patterns in flowers that are hidden from human eyes. A magnet points toward an invisible field. Our senses are useful, but they are not complete. They are windows, not the whole sky. This is why the fifth dimension is such a powerful idea. It asks whether the universe might have parts that are not missing, not imaginary, not spiritual, but physically present, and simply beyond our direct access. It suggests that what looks like empty space might have hidden depth. It suggests that forces we do not fully understand may be shaped by geometry we cannot see. It even suggests that gravity, the most familiar and stubborn of forces, the force that keeps your feet on the floor and your pillow on the bed, may be quietly connected to space beyond the 3 dimensions we know. There is something almost comforting about this in a strange way. We often imagine science as a process of shrinking mystery, of explaining things until nothing surprising remains. But the real history of science has often done the opposite. Every answer opens a larger room. Earth was not the center of everything. The stars were not tiny lamps in a dome. The Milky Way was not the whole universe. Matter was not solid in the simple way it seemed. Time was not the same for everyone. Again and again, reality turned out to be larger, stranger, and more subtle than common sense allowed. A fifth dimension belongs to that same tradition. It does not say that our world is fake. It says our world may be part of something wider. And if that sounds too strange, remember that we already live with an invisible dimension every day. Time is often treated as the 4th dimension, not because it is the same as space, but because it is deeply linked with it. You cannot describe an event only by saying where it happened. You must also say when. A cup falling from a table is not just a location in space, It is a sequence. It was on the table. Then it tipped. Then it fell. Then it met the floor with a sound that probably made someone in the next room ask if everything was all right. Without time, there is no story of motion. There is only a frozen arrangement. Einstein showed that space and time are not separate stage props. They're woven together into space-time. That alone was already a huge shift in human understanding. The universe was not a rigid container with one universal clock ticking behind it. It was something flexible, something responsive, something that could be curved by matter and energy. Once that idea entered physics, it became natural to wonder whether even space-time might be part of a deeper structure. Perhaps the fourth dimension was not the final surprise. Perhaps the fifth was waiting quietly behind it. The idea did not appear from nowhere. In the early 20th century, some physicists began to notice something remarkable. If they imagined an extra dimension beyond the familiar ones, certain forces that seemed separate could start to look connected. Gravity and electromagnetism, two great pillars of nature, might be described as different features of a larger geometry. It was an elegant dream. Maybe the universe was not a collection of unrelated rules. Maybe some of its forces were shadows of a higher dimensional shape, like seeing different shadows on a wall and slowly realizing they come from the same object turning in the light. That shadow idea matters. A higher dimensional thing can cast a lower dimensional shadow. A sphere passing through a flat plane would appear as a point, then a growing circle, then a shrinking circle, then nothing. A creature living in that plane might never see the whole sphere. It would only see slices. It might invent laws to describe the circles, never knowing they were glimpses of something larger. In the same way, perhaps the things we see in our universe are slices of a deeper reality. Perhaps particles, forces, and fields are not separate little objects in the simple sense, but signs of something moving through dimensions we cannot enter. This is not a claim that everything is solved. Far from it. The fifth dimension is not something scientists have held in a jar or photographed with a telescope. It remains an idea explored through mathematics, experiments, and the search for clues. It may be curled up too small to detect. It may be large but hidden because we are confined to a kind of cosmic surface. It may not exist at all in the way some theories suggest. Physics must always keep that honesty. Wonder is not the same as proof. A beautiful idea still has to answer to the universe. Nature is under no obligation to be impressed by our imagination, and yet the idea persists because it offers possible ways to think about some of the deepest puzzles we face. Why is gravity so much weaker than the other forces? Why does the universe contain forms of matter and energy we cannot see directly? Why do the laws of physics have the shapes they do? Why does reality seem so finely structured, so mathematical, so oddly willing to be described by geometry? Extra dimensions have appeared in attempts to build a deeper theory of nature, especially in ideas that try to bring gravity and quantum physics into the same room without causing them to glare at each other from opposite corners. That may be one of the great motivations behind the fifth dimension. Modern physics has two enormous successes that do not fit comfortably together. On the larger scales, general relativity describes gravity, black holes, expanding space, and the sweeping architecture of the cosmos. On the smallest scales, quantum physics describes particles, uncertainty, fields, and the strange behavior of matter and light. Both work beautifully in their own domains. Both have passed astonishing tests. But when we try to combine them completely, especially in places where gravity is intense and quantum effects matter, the picture becomes difficult. A fifth dimension or even more hidden dimensions may offer a way to make the pieces fit, not by adding fantasy but by changing the shape of the puzzle. Think of trying to solve a knot in a piece of string while only seeing its shadow on a wall. The shadow may look impossibly tangled. Lines cross in ways that seem confusing. But if you could lift the string away from the wall and view it in 3 dimensions, the knot might make more sense. You could see what passes over and what passes under. You could loosen it. Perhaps some problems in physics look impossible because we are seeing their shadows in too few dimensions. Perhaps the deeper structure is not more complicated but more spacious. There is a quiet humility in that thought. We often assume that the world we perceive is the world as it is. But every scientific revolution has reminded us that perception has a starting point, not a final verdict. The sun appears to move across the sky, but Earth is turning. A table feels solid, but most of its atomic structure is empty space held together by forces. Time feels steady, but speed and gravity can change its pace. Space feels simple, but it may bend and stretch. So maybe, just maybe, the number of dimensions we experience is another place where intuition is only partly right. Tonight, we will move slowly through that possibility. We will begin with the space we understand, the ordinary world of length, width, and height. Then we will ask what a dimension really is without rushing into complicated mathematics. We will visit simple imagined worlds like flat surfaces and shadows because they help us think about things we cannot directly picture. We will follow the path from Einstein's space-time to the old dream of a hidden, curled-up direction. We will meet the idea that our universe could be like a thin sheet floating in a larger space. We will wonder whether gravity might leak into places we cannot go. And we will ask whether the fifth dimension is a real feature of nature, a useful mathematical tool, or a sign that our current view of reality is still incomplete. For now, all we need is the first quiet step. Look around if your eyes are still open. Notice the distance between objects, the edge of a blanket, the shape of a doorway, the small gap between your hand and whatever it rests beside. This is space as the body knows it, familiar, practical, dependable. And yet, hidden behind that familiarity may be a question large enough to unsettle the whole universe. Is there another direction beside us? Not above or below, not forward or back, but somehow beyond the map our senses can draw. It may be that reality is exactly as wide as it appears. It may be that the three dimensions of space and the dimension of time are all the universe needs. But physics has learned to be cautious around words like obvious. The obvious has failed before, and when the universe hides something, it often does so in plain sight, not by making it distant, but by making it too close, too subtle, or too deeply woven into everything for us to notice at first glance. A fifth dimension, if it exists, may not be somewhere else. It may be here, touching every point in space, folded into the quiet structure of the room around you, present in the fall of gravity, the behavior of particles, and the vast shape of the cosmos. So let the idea sit gently for a moment. You do not have to picture it perfectly. No one really can. Higher dimensions are difficult because the mind was trained by tables, roads, trees, and rooms, not by hidden geometry. But we can approach the thought carefully. We can build it from simple pieces. We can let the familiar world become slightly less familiar. And from there, we can begin to see why some physicists have wondered whether our universe is not a sealed box but a visible surface of something deeper, something wider, something still waiting beyond the directions we know. The first thing to notice about space is how ordinary it feels. It is so familiar that we hardly notice it at all. You wake up in a room, you know where the door is, you know where the ceiling is. You know that if you reach to the side, your hand will move sideways, not vanish into some unknown direction that has never appeared on a map. The world behaves with a kind of everyday reliability. A chair stays under you, a lamp stays on the table. Your pillow does not drift through an invisible doorway into a higher reality, at least not usually, unless you have a very determined cat. This ordinary space is the world our senses were built to handle. We do not need a physics degree to move through it. A child learns it before learning the names for it. Reach, crawl, stand, walk, climb, fall, bump into furniture, learn from the furniture, try again. The body learns direction through contact. It discovers that some things are near and some are far. It learns that a step forward changes what the eyes see. It learns that turning the head changes the whole room. Long before we speak about dimensions, we live inside them. We usually describe this familiar space in three ways. There is length, the direction along which a road stretches ahead. There is width, the direction from side to side. There is height, the direction from the floor to the ceiling, from the ground to the branches of a tree, from the surface of the sea to a bird moving above it. These directions are not just ideas in the mind. They are the practical map of being alive. They tell your hand how far to reach for a cup. They tell your feet how to climb stairs. They tell your eyes how to judge whether a doorway's open, closed, or just slightly too narrow when carrying a box that seemed much smaller a moment ago. Because these three directions are everywhere in daily life. They feel complete. They feel final. If someone asks where something is, we can answer by giving its place in space. It is across the room, on the shelf, behind the book, under the blanket, above the fireplace, beside the window. We do this so naturally that it rarely occurs to us that our language is built from the directions our bodies can access. Even memory is full of space. We remember places as arrangements. We picture childhood homes, school corridors, roads, gardens, kitchens, and the particular corner where something important happened. Our minds store experience inside rooms and landscapes, yet the same everyday confidence can make space seem simpler than it really is. We treat space as empty background, as if it were nothing more than a container for things. Put a mug on a table and we think about the mug and the table, not the space between them. Look at the night sky and we think about stars, not the dark distances separating them. Walk across a room and we think about the motion, not the invisible structure that allows motion to occur. Space is so quiet that it is easy to mistake it for nothing. But physics has learned that space is not just nothing. It is not a blank stage that sits there while matter performs. It has properties. It can be measured. It can stretch as the universe expands. It can curve around massive objects. It can carry waves in the form of ripples in space-time. It participates in the behavior of reality that is already strange. The floor beneath you may seem firm, the room may seem still, but on the largest scale, space itself is part of the story, not just the place where the story happens. The visible world gives us a strong impression of completeness, but our senses only collect certain kinds of information. The human eye sees a narrow band of light. The ear hears a limited range of vibration. The skin detects pressure, heat, cold, and pain, but not the full structure of the physical world. We are surrounded all the time by things we do not directly sense. Radio waves pass through the room. Magnetic fields shape compass needles. Neutrinos stream through your body from the sun in numbers too large to picture, and you do not feel a single one. The world we can see is not the same as the world that exists. This is an important starting point for thinking about hidden space. We already accept that reality contains things beyond ordinary perception. We do not see the air unless dust or mist reveals it. We do not see ultraviolet light, yet some insects use it to navigate flowers. We do not feel Earth spinning, though it carries us around with steady persistence. We do not notice the gravitational pull of the moon tugging the oceans unless we watch the tides. The hidden parts of nature are not hidden because they are magical. They are hidden because our senses were shaped for survival, not for complete cosmic reporting. A fifth dimension, if it exists, would be hidden in a more difficult way. It would not be like infrared light, which can be detected with the right instrument. It would not be like a distant planet that can be found with a better telescope. It would be hidden as a direction, a way space itself might extend, but a way that we do not experience directly. That makes it hard to imagine because imagination usually borrows from what the body knows. We can picture mountains, oceans, planets, tunnels, and rooms. But when we try to picture another direction that is not left, right, forward, backward, up, or down, the mind reaches for a handle and finds none. Still, we can approach the problem gently. Think first about a line. A creature living on a line would know only one direction. It could move forward and backward. Its whole universe would be like a thread. If another creature could step off the line, move around it, and return at another point, the line creature would have no natural way to describe that journey to it. The visitor might disappear from one place and reappear somewhere else. Nothing supernatural would have happened. The visitor simply used a direction the line creature could not access. Now, think about a flat surface. A creature living on that surface could move forward and backward, left and right, but not upward. Its universe would have length and width, but no experienced height. If you placed your finger through that surface, the creature might not see a finger as we know it. It might see only a changing cross-section, perhaps a shape appearing from nowhere, growing, shrinking, and vanishing. The full object would remain beyond its world. The creature would not be stupid. It would simply be limited by the geometry of its own existence. These examples are simple, but they help us understand the difference between what exists and what can be experienced from within a lower dimensional world. If a higher direction exists, beings confined to fewer directions may only see effects, traces, shadows, or slices. They may build laws around those effects without knowing the larger shape causing them. They may become very good at predicting what happens in their world while still missing the wider space around it. This is where our own situation becomes interesting. We are not floating outside the universe looking down at it from some perfect viewpoint. We are inside it. Every measurement we make is made from within. Every instrument we build is built from matter that belongs to the same universe we're trying to study. That does not make science weak, it makes science careful. It means that if there are hidden dimensions, we may not be able to see them directly. We may have to infer them from their influence, the same way we infer air from wind, gravity from falling, or distant planets from the wobble of a star. The world we can see is therefore both real and incomplete. A mountain is real, a candle flame is real, the moon above a dark roof is real, but each is only the visible face of deeper structures. The mountain is made of atoms, the flame is chemistry and heat and light. The moon follows a curved path through space-time. The simple surface of things hides layers of explanation. A fifth dimension would be another layer, not replacing the visible world, but deepening it. One reason the idea is so difficult is that we usually confuse invisibility with distance. If we cannot see something, we imagine it far away, like a galaxy beyond our telescope or a cave beyond a hill. But a hidden dimension would not have to be far away. It could be present at every point in ordinary space. It could be closer than your own hand, not in front of it or behind it, but connected to it in a direction you cannot point toward. That is a strange thought, but not meaningless. It suggests that the hidden part of space might be woven into the visible part, like a thread too fine to notice in a fabric that still affects the pattern. Some theories imagine an extra dimension curled up extremely small. If a direction is curled tightly enough, moving through it may be impossible for large objects like people, planets, or teacups. A tiny particle, however, might be affected by it. Imagine a long garden hose seen from far away. From a distance, it looks like a simple line stretching across the grass. An ant on the hose, however, could move not only along its length, but also around its circular surface. What looks one-dimensional from far away has an extra direction up close. In a similar way, space might contain tiny curled directions that are invisible at human scales, but important in the behavior of particles. This is only an analogy, of course. The actual mathematics is much more precise and much less likely to involve garden hoses, but the basic idea is useful. A dimension can be hidden not because it is absent, but because its scale is too small for us to notice. If you cannot resolve the curled part, the world looks simpler than it really is. Like looking at woven cloth from across a room and seeing only a smooth surface, then looking under a magnifying glass and discovering crossing threads. Other theories imagine a different kind of hiding. Perhaps our visible universe is like a vast sheet, sometimes called a brain, embedded in a larger space. In that picture, the particles and forces we know may be confined to the sheet, while gravity might have access to the larger surrounding space. We would experience our world as three-dimensional because everything we are made of is tied to it. We would not feel trapped because all the directions available to matter would still be available to us. But there could be another dimension nearby in a physical sense beyond our reach because our matter cannot move into it. This can sound like science fiction, and in many ways it has inspired science fiction. But its origin is not fantasy. It comes from attempts to solve real problems in physics. Why gravity is so weak compared with other forces, how to connect the physics of the very small with the physics of the very large, how to understand the structure of particles and fields. Extra dimensions are not added just to make the universe feel mysterious. They appear because certain mathematical frameworks seem to need them, or because they allow different parts of physics to fit together in ways they otherwise do not. Of course, needing an idea in mathematics does not automatically mean nature uses it. This is where the caution matters. Physics is filled with beautiful ideas that may or may not describe the actual universe. The fifth dimension is not something we can simply assume. It must leave evidence. It must produce effects that can be tested. Scientists look for signs in particle collisions, in gravity experiments, in cosmology, and in the behavior of forces at tiny scales. So far, no clear proof has arrived. The fifth dimension remains a possibility, not a confirmed room in the cosmic house. But even as a possibility, it changes how we think. It reminds us that the visible world may not be the full world. That is not a failure of human perception. It is just the normal condition of being a physical creature. A fish in deep water may know currents, pressure, darkness, and the shapes of nearby things, but not the clouds above the surface. A person in a valley may know the hills, but not the whole continent. A mind evolved on Earth may know the space useful for walking, reaching, building, and sleeping, but not every structure reality contains. There is a quiet lesson here about scale. At human scale, the world appears solid and complete. At atomic scale, it becomes mostly empty structure held together by forces. At cosmic scale, space expands, galaxies drift, and the universe has a history measured across billions of years. At extremely high energies or tiny distances, perhaps space itself changes character again. Perhaps dimensions that are hidden from ordinary life become relevant. The fact that we do not see them at breakfast says very little about whether they exist in the deep architecture of nature. Think about a familiar object like a book. To your eyes, it is a simple three-dimensional thing with a front cover, a back cover, and pages between. But the story inside adds another kind of structure. You can hold the whole book at once, but you read it one page at a time. The full object exists, yet your experience moves through it in sequence. Now imagine that reality also has structures we do not experience all at once. The surface may be available to us while the deeper arrangement remains hidden, affecting what we see without being directly seen. The comparison is not perfect, but it helps show how something can be present and inaccessible at the same time. The space we cannot see may also help explain why physics often sounds stranger the deeper it goes. Our everyday intuitions are trained in the middle world, the world of hands, houses, weather, and walking distances. But the universe is not required to follow middle world habits at every scale. Quantum particles do not behave like tiny billiard balls. Black holes do not behave like ordinary dark objects. Time does not behave like a universal clock. Space then may not behave like an empty box. It may have layers, folds, limits, and hidden directions. The fact that this feels strange is not a reason to reject it. It is a reason to move slowly. Moving slowly is especially important because words can mislead us. When we say fifth dimension, it is easy to imagine a spooky realm, a parallel hallway, or a secret place where lost socks have been gathering for centuries. But in physics, a dimension is more practical than that. It is a direction or a degree of freedom needed to describe something. The hidden dimension would not necessarily be a world of ghosts or copies of ourselves. It would be part of the geometry that determines how fields, particles, and gravity behave. It may be less like another room and more like a property of the room you are already in. This is why the world we can see is such a useful starting point. We do not have to abandon it. We begin with what is familiar and ask what must be added to explain it more fully. The three directions of space work beautifully for ordinary life. They're enough to build homes, launch airplanes, describe the motion of planets, and arrange furniture badly before arranging it slightly better. But when physicists ask the deepest questions, familiar space may not be enough. The visible world may be the accessible part of a wider structure. The hidden part, if it exists, would not make everyday life less real. Your room remains your room. Your bed remains your bed. Gravity still pulls gently downward. Morning still arrives with its usual lack of concern for whether anyone is ready. But beneath that daily stability, there may be a deeper geometry, one that only reveals itself under extreme conditions or through subtle effects. It is like hearing a faint note in a piece of music and realizing there may be an instrument playing somewhere behind the main melody. So when we speak of the universe hiding a fifth dimension, we are not saying reality is pretending. We are saying that nature may have structure beyond direct human access. The world we see may be a slice, a surface, a projection, or a low-energy version of something larger. And if that sounds humbling, it should. The history of physics is full of moments where the human viewpoint had to grow wider. The Earth became a planet, the Sun became a star, the Milky Way became one galaxy among many, matter became fields and particles, space became space-time. Perhaps the next step, if the evidence ever leads there, is that space-time itself becomes part of a larger dimensional structure. For now, we stand in the familiar room of three-dimensional space and look carefully at its walls. Not because we expect to see a glowing doorway, but because the most important clues in physics are often subtle. A tiny mismatch in an experiment, a force weaker than expected, a particle behaving in a way that hints at deeper rules, a mathematical pattern that keeps returning. The unseen world does not usually announce itself loudly. it leaves traces, and so the visible world becomes a kind of invitation. Every distance, every shadow, every motion through ordinary space reminds us of the question beneath the question. What does it mean for something to have a direction? What does it mean for space to be extended? Why are there 3 large spatial directions instead of 2 or 4 or more? The answer is not obvious. It only feels obvious because we have never lived anywhere else. A creature born in a 3-dimensional world may naturally assume 3 dimensions are the only sensible option. But the universe may not be built around what feels sensible to creatures who learn geometry by reaching for cups and avoiding walls. That is where the next step begins. Before we can think clearly about a hidden 5th dimension, we need to slow down and ask what a dimension really is. Not as a dramatic mystery, not as a science fiction doorway, but as a simple idea about freedom, position, movement, and description. Because once that idea becomes clear, the thought of an unseen direction becomes less like a magic trick and more like a careful extension of something we already understand. To understand why anyone would even suggest a hidden 5th dimension, it helps to slow down and ask what a dimension really is. The word sounds grand, almost like it belongs to a locked cabinet in a university basement beside chalkboards covered in mysterious symbols and one very cold cup of forgotten coffee. But at its heart, a dimension is not meant to be intimidating. It is a way of describing freedom. It tells us how many independent ways something can vary, how many directions are needed to locate it, how many choices the universe gives an object when it moves. Start with the simplest possible world. Imagine a tiny bead sliding along a perfectly straight wire. It cannot leave the wire. It cannot jump off to the side. It cannot rise above it or dip below it. It has only one kind of freedom. It can move this way or that way along the wire. To describe where the bead is, you only need one piece of information: how far along the wire it has gone. That is one-dimensional motion. It is not one-dimensional because the bead itself has no thickness in a real physical sense, or because the wire is truly perfect. It is one-dimensional because the motion available to the bead has only one independent direction. Now imagine an ant walking across a tabletop. The ant can move forward and backward, but also left and right. It can explore the surface in 2 independent directions. To say where the ant is on the table, one piece of information is not enough. You need to know how far across and how far along. That is what we mean by a 2-dimensional surface. The ant may be a 3-dimensional creature in reality, with height and little legs and a personality perhaps more determined than polite. But if we only care about its path across the flat tabletop, the useful description is 2-dimensional. Then we come to our ordinary space. A bird in the air, a fish in the sea, a dust mote drifting in sunlight, or a person searching for their glasses while wearing them all occupy 3-dimensional space. To locate something fully, we need 3 independent pieces of information: how far one way, how far another way, how far upward or downward. These 3 directions allow objects to pass around one another, stack above one another, hide behind one another, and generally make the world as richly inconvenient as it is. A room has corners because space has 3 dimensions. A box can contain things because it has length, width, and height. A maze can be confusing because there is enough room for turns, walls, and the occasional regret about entering it in the first place. But here is the important part. A dimension does not have to be something our eyes can picture easily. It is not always a physical direction like up or left. In mathematics and physics, a dimension is often a degree of freedom, a necessary part of description. If you want to describe the state of a moving object, you may need to know not only where it is, but how fast it is moving and in what direction. If you want to describe the weather, you may need temperature, pressure, humidity, wind speed, and more. Those are not spatial dimensions in the everyday sense, but they are dimensions of a description. They're independent quantities that help define a situation. This matters because when physicists talk about a 5th dimension, they are not simply adding another hallway to the universe because 3 directions felt a little plain. They're asking whether nature requires an additional degree of freedom, something beyond ordinary space and time to describe itself completely. It may be a direction in a deeper geometry. It may be curled, hidden, or inaccessible to familiar matter. It may appear only in equations that try to unite different forces. But the basic idea begins with the same simple question: How many independent ways does reality need in order to be fully described? For everyday life, 3 spatial dimensions are enough. If you want to find a book in a room, you need to know where it is from side to side, where it is from front to back, and how high it is. If the book is on the floor under the bed, you may also need patience and perhaps a flashlight. But the geometry itself is straightforward. However, if you want to describe an event, not just an object, you need something more. You need to say when it happened. The book fell from the shelf at a certain moment. The kettle boiled at a certain moment. Someone decided to reorganize a drawer and immediately regretted it at a very specific moment. Time gives events their place in the unfolding story. This is why modern physics treats time as deeply connected with space. We often say that time is the 4th dimension, though it is not just another spatial direction you can stroll into after breakfast. You cannot move freely through time the way you can move across a room. You cannot decide to take 2 steps toward last Tuesday, which is probably for the best considering how many people would spend all afternoon fixing small mistakes and never get anything done. But time is still needed to locate events. Without it, the universe would be like a photograph with no before or after. Motion would vanish. Change would vanish. Cause and effect would have nowhere to unfold. Einstein showed that space and time are woven together in a way that changed physics forever. Before that, many people thought of space as one thing and time as another. Space was where things happened. Time was when they happened. Simple enough. But relativity revealed that different observers moving in different ways can disagree about measurements of space and time while still agreeing on the deeper structure connecting them. This does not mean reality is random or that anything goes. It means that space and time are not as separate as they feel. They form a single framework, and the measurements depend on motion and gravity. Once that idea entered physics, the word dimension became more flexible in the scientific imagination. The universe was no longer just a 3-dimensional stage with a clock ticking above it. It was a 4-dimensional structure with time included as part of the fabric. And if time could be understood as part of geometry, maybe other features of nature could be understood geometrically too. Maybe forces that seemed separate were not separate in a deeper view. Maybe electromagnetism, gravity, and the behavior of particles were different signs of a larger dimensional pattern. This is where the 5th dimension begins to seem less like a wild leap and more like a question physics was almost forced to ask. Still, the mind resists it. It is easy to say 1 dimension, 2 dimensions, 3 dimensions, 4 dimensions, and then a 5th. It is much harder to picture what that means. Our imagination works by borrowing from experience. We can imagine another room because we have seen rooms. We can imagine another planet because we have seen landscapes and pictures of worlds. But another spatial direction beyond all known directions is different. There is no ordinary image for it. If you try to point toward it, your hand will always choose one of the directions it already knows. Forward, back, side, up, down. The hand is loyal to 3-dimensional space. It has never been trained for anything else. This limitation does not make the idea meaningless. It only means that visualization has reached its edge. Mathematics often goes beyond what the senses can picture. A sailor may understand a curved Earth long before seeing it from space. A physicist may understand curved space-time without picturing it as a literal rubber sheet. A musician may understand harmony without seeing sound waves in the air. Human thought can use patterns, relationships, and consequences even when imagination struggles to form a neat picture. In fact, many of the most successful ideas in physics began as things no one could comfortably imagine. A dimension then is not defined by whether we can draw it on paper. It is defined by whether it is needed, whether it has consistent rules, and whether those rules help explain or predict what nature does. If a 5th dimension exists, it would have to be more than a dramatic phrase. It would need to be part of a theory with consequences. It might change how gravity behaves at small distances. It might leave tiny signatures in particle experiments. It might affect the early universe. It might explain why certain forces have the strength they do. Or it might remain only a beautiful mathematical path that nature itself does not take. Physics has to keep both possibilities open. One helpful way to understand dimensions is to think about constraints. A creature may live in a space with more dimensions than it can use. A train travels through 3-dimensional space, but its track restricts it to almost 1-dimensional motion. A bead on a necklace moves mostly along a curve. A person walking on Earth moves mostly across a surface, even though the world has depth above and below. A fly, less respectful of household boundaries, uses the room more fully, so the dimension of the larger space and the dimension available to a particular object are not always the same. This is a quiet but important distinction. It gives us a way to think about hidden dimensions. Perhaps the larger universe has more directions than the ones matter can easily move through. We may be like objects confined to a track, not because the wider space is absent, but because the rules holding our particles together keep us within a certain slice of it. If all our instruments, bodies, and atoms are made of particles confined to that slice, then we would naturally experience the slice as the whole universe. We would not feel walls around us. We would simply never have access to the direction beyond the slice. A fish born in water does not feel water as a prison. It feels it as the world. Another important idea is scale. A dimension can be hidden if it is extremely small. The garden hose example is often used because it is simple and useful. From far away, a hose looks like a line. A small insect on it, however, can crawl around its thickness. What appeared to have only one direction actually has another, but the second direction is too tiny to notice from a distance. In some theories, extra dimensions may be curled up at scales far smaller than atoms. We do not notice them because everything in ordinary life is too large to resolve their shape, but small particles might still be influenced by them. The way a tiny traveler detects paths that a giant would never see. This idea of a curled dimension is strange but not careless. It shows how a dimension can be real without being large. We usually think dimensions must stretch openly like the three spatial directions we know, but mathematics allows a direction to loop back on itself. If you move far enough along it, you return to where you started. A circle is like that. Walk around a ring and you arrive back at the beginning. If an extra dimension were curled into a tiny loop at every point in space, it could be present everywhere while remaining inaccessible to large-scale motion. The room around you could contain that hidden structure at every point and still look perfectly ordinary. There is another way to think about it. Imagine a carpet. From across the room, it looks flat and smooth. But if you kneel close, you see fibers, loops, and gaps. The surface has small structures that were invisible at larger scale. You did not have to travel to another universe to find them. You only had to look more closely. In physics, the question is whether space-time itself may have hidden structure at scales far beyond current direct experience. Perhaps what seems smooth to us is actually shaped by tiny geometry. Perhaps the familiar three dimensions are the large directions, and the extra ones are the small ones tucked into the weave. But there is also the possibility of a large hidden dimension not curled up in the same way but separated from us by the way particles and forces behave. In some theories, our universe is like a membrane within a higher dimensional space. The ordinary particles of matter are stuck to this membrane while gravity may move through the larger space. If true, this could help explain why gravity seems so weak compared with other forces. Maybe gravity is not weak in itself. Maybe some of it spreads into dimensions we do not experience, diluting its effect in our world. It is a bold idea and not proven, but it shows how the meaning of dimension can be tied to real physical questions. Notice how different this is from simply imagining a fantasy realm beside our own. In physics, a hidden dimension is not added for decoration. It must do work. It must explain something, connect something, or make a theory more consistent. The fifth dimension may be a way of making gravity and electromagnetism look like parts of a single geometry. It may be part of a larger attempt to combine quantum physics with gravity. It may help organize the behavior of particles. The question is always whether the extra dimension gives nature a deeper simplicity that is not visible from our ordinary viewpoint. This idea of deeper simplicity is worth lingering on. Sometimes a problem looks complicated only because we are viewing it from the wrong angle. A shadow on the wall can change shape in confusing ways, but the object casting it may be simple. A knot can look impossible from one side but loosen when seen from another. A map of a mountainous road may look like a twisting line, but in the landscape itself, the curves make sense because they follow hills and valleys. Extra dimensions may work like a new angle of view. They may reveal that forces or particles that seem unrelated in our world are connected in a larger structure. Of course, the fact that something is elegant does not make it true. The universe has a way of accepting some elegant ideas and ignoring others completely. Nature is not a committee trying to please physicists. A fifth dimension must face experiment. If it affects gravity, we should try to measure gravity at tiny distances. If it affects particles, we should look for missing energy or unusual patterns in collisions. If it shaped the early universe, we should search the sky for traces in cosmic structure. This is the difference between scientific imagination and pure invention. Science is allowed to imagine boldly, but then it must ask how the imagination touches the world. There is a comforting honesty in that. The fifth dimension is not presented as a known place with a sign on the door. It is a possibility, a question, a mathematical opening that may or may not correspond to physical reality. And that is all right. Much of physics lives in that space between what is known and what might be. The important thing is not to pretend certainty, but to understand why the idea exists. It exists because dimensions are not just directions we can point to. They are the framework of description. If our current framework cannot explain everything, perhaps it is missing a degree of freedom. The word dimension also carries emotional weight because it reminds us that our experience is limited. We do not like to think of ourselves as limited creatures. We prefer to imagine that if something is real, we should be able to see it, touch it, or at least build a very expensive machine to detect it. But reality has never promised to be fully available to human senses. The history of science is a history of finding hidden layers, microscopic life, invisible radiation, atomic structure, curved space-time, quantum fields. The hidden is not unusual. The hidden is normal. The visible world is only the part that greets us first. So what does a dimension really mean? It means a way something can be. It means a direction of variation, a freedom of movement, a coordinate of description, a piece of the structure needed to say what is happening. In ordinary space, it means length, width, and height. In space-time, it includes time as part of the description of events. In deeper theories, it may include additional directions not directly available to us. The fifth dimension is not simply after the fourth like another stair on a staircase. It is a possible extension of the way reality is organized. This is why it helps to approach the idea without forcing the mind to draw it. You do not need to picture a fifth direction the way you picture a hallway. You only need to understand that our ability to picture things is based on survival in three-dimensional space, not on the full range of mathematical possibility. The mind can still reason carefully. It can ask what would change if another dimension existed. It can look for signs. It can build analogies from lower dimensional worlds. It can admit when the analogy is imperfect and still use it as a stepping stone. A dimension is also relational. It is not always meaningful by itself. A direction matters because it allows differences between places, paths, events, or states. If nothing could vary along a dimension, it would leave no trace. That is why a hidden dimension must have some effect if it is to belong to physics. It must influence the shape of fields, the motion of particles, the strength of forces, or the history of the universe. Otherwise, it would be beyond not only our senses, but also scientific discussion. A dimension that changes nothing is like a silent clock in a universe where nothing happens. It may be an idea, but not a physical actor, and yet even the possibility is enough to change the feeling of the room around us. The space between you and the wall seems simple, a small distance, a quiet gap. But physics asks whether each point in that gap may contain more structure than appears. Not a hidden doorway in the ordinary sense, not a place where you could misplace your slippers and recover them through higher geometry, but perhaps a tiny curled direction or a relation to a larger space, or a sign that our familiar world is only the low-energy surface of something deeper. The ordinary room becomes ordinary and mysterious at once. This is one of the gentle pleasures of physics. It does not always take you away from daily life. Sometimes it returns you to daily life with new attention. A table is still a table, but also a cloud of atoms. A clock is still a clock, but also a measure of space-time. A shadow is still a shadow, but also a reminder that higher shapes can leave lower traces. A dimension is still a practical tool for locating things, but also a doorway into the question of how wide reality really is. So before we ask whether the universe may hide a fifth dimension, we first learn to loosen the word dimension from the narrow grip of ordinary vision. It is not just a visible direction. It is a kind of freedom. It is part of the grammar of nature. The three dimensions of space tell matter where it can go. Time tells events how they unfold. A fifth dimension, if it exists, may tell us why some forces behave the way they do, why gravity has its strange character, or why the universe looks complete while perhaps being only one face of a larger structure. The next helpful step is to imagine what a hidden dimension would look like to creatures who could not enter it. Since we cannot easily picture higher space directly, we can learn by stepping downward. Instead, we can imagine flat worlds, shadows, slices, and surfaces. We can watch how a three-dimensional object would appear to a two-dimensional being, and from that begin to understand how a fifth-dimensional reality might leave traces inside our own. Not perfect pictures, not final answers, but careful little lanterns held up against a darkness that may not be empty at all. Imagine a world that is perfectly flat. Not just flat like a table or flat like a sheet of paper lying on a desk, but truly flat. A world with no height at all. No ceiling, no sky, no stairs, no hills, no depth beneath the ground, no birds passing overhead, no cupboards to reach into, and no unfortunate moments where you stand up too quickly and bump your head. In this world, there is only forward and backward, left and right. Every creature, every house, every road, every object exists on a surface and can only move along that surface. To the beings who live there, this would not feel strange. It would feel complete. It would be their normal. Such a world helps us because it gives the mind a smaller problem to hold. We cannot easily picture a fifth spatial direction beyond our own because every image we make still uses the three directions we know. But we can imagine a two-dimensional world and then ask how a three-dimensional object would appear inside it. By stepping down one level, we get a useful comparison. We do not solve the whole mystery, but we make it less slippery. We give the imagination a practice room. Picture a flat creature living in this flat world. Perhaps it is shaped like a little circle or a square or a narrow triangle with very good manners. It moves across its surface, meets other flat creatures, avoids flat obstacles, builds flat homes, and measures flat distances. It knows nothing of above or below because there is no above or below in its experience. If you try to explain height to it, you might have a difficult conversation. You could say, there is a direction outside your world. The creature might reply, outside where? You could say, not to the left, not to the right, not ahead, not behind, but up. The creature might pause politely and then assume you had eaten something unusual. This is the first trouble with higher space. A being limited to fewer dimensions cannot easily picture the larger world that contains it. It may be intelligent, careful, and scientific, but its imagination is trained by what it can experience. If all motion has always happened along a flat surface, then any direction beyond that surface sounds impossible. Not because the direction is impossible, but because the creature has no sensory history for it. It has no memory of climbing. It has no view from above. It has never lost a ball under a sofa because there are no sofas with undersides, which may at least make cleaning easier. Now imagine that you, as a three-dimensional visitor, bring a sphere into this flat world. You do not place it on the surface like a ball resting on a table. Instead, imagine the sphere passing through the flat plane itself. The flat creatures cannot see the whole sphere. They cannot look upward at its roundness. They can only see the part of the sphere that intersects their world at any given moment. At first, when the sphere just touches the plane, the creatures see a tiny point appear from nowhere. Then, as the sphere moves farther through, the point becomes a small circle. The circle grows larger and larger. Then it begins to shrink. Finally, it becomes a point again and disappears. To the flat creatures, this would be astonishing. Something appeared without entering from any known direction. It changed size without any visible cause. It vanished without traveling away. They might develop a theory of mysterious expanding circles. They might argue about whether the circle was alive, whether it broke the laws of nature, or whether someone had spilled a very unusual drop of ink into reality. But from our view, nothing magical happened. A sphere passed through a plane. The flat world saw only slices. This is one of the most useful ideas for thinking about higher dimensions. A lower dimensional world may not see the whole object. It may see a cross-section, a slice, a shadow, a trace. If a higher dimensional object passed through our three-dimensional space, we might not see the whole thing either. We might see changing three-dimensional sections that appear, transform, and disappear in ways that would seem deeply strange. A four-dimensional object moving through our space could look as puzzling to us as the sphere looked to the flat creatures. We would not be foolish. We would simply be inside the wrong number of dimensions to see the full object at once. This is why people often use shadows when explaining higher dimensions. A three-dimensional object can cast a two-dimensional shadow. Hold a cube in sunlight and its shadow appears on the ground as a flat shape. The shadow may look like a square, a stretched rectangle, or a strange angled figure depending on how the cube is turned. The shadow is related to the cube, but it is not the cube. It leaves out depth. It compresses the object into fewer dimensions. If a flat creature studied only the shadow, it might learn patterns. It might notice that the shape changes when the object turns, but it would not directly see the object itself. In the same way, some scientists and mathematicians use projections to study objects with more dimensions than we can picture. A higher dimensional shape can be represented by a lower dimensional shadow. You may have seen drawings of a cube inside another cube with lines connecting the corners. This is often used as a projection of a four-dimensional cube, sometimes called a tesseract. But the drawing is not the real object, just as a square shadow is not a real cube. It is a helpful trace, a way to let the mind work with something it cannot fully see. It is like a map of a city. Useful, yes, but you cannot smell the bakery from a map, and you cannot trip over a curb on it either. The trouble is that our minds tend to mistake the projection for the thing itself. We look at a drawing of a higher dimensional object and try to imagine it as a strange three-dimensional cage. Then we feel confused because the drawing is asking our three-dimensional imagination to do a job it was not built to do. The better approach is to remember what a projection is. It is a compromise. It gives up some information so we can represent something beyond direct vision. It is not supposed to feel natural. It is a tool, not a window you can climb through. Flat worlds also teach us something about hidden movement. Suppose a three-dimensional visitor reaches into the flat world and lifts a flat creature out of its surface. From the viewpoint of the other flat creatures, their friend has vanished. The friend did not move left or right. It did not go forward or backward. It simply disappeared from every direction they understand. Then if the visitor places that creature somewhere else on the surface, it reappears in a new location. To the flat beings, this might look like teleportation. From the higher dimensional viewpoint, it is just a shortcut through a direction the flat world cannot access. This example is tempting because it makes higher dimensions sound like secret passages. And in some mathematical settings, extra dimensions can act a little like that. But we should be careful. A hidden fifth dimension in physics is not automatically a convenient tunnel for people, spaceships, or missing television remotes. If it exists, ordinary matter may not be able to move freely through it. It may be curled too small, or particles may be confined to the familiar dimensions by the rules of fields and forces. The analogy helps us understand the concept, but it does not grant us a working higher dimensional elevator, which is probably just as well. Most of us already struggle with normal elevators when someone presses every button. Still, the lesson is powerful. What looks impossible inside one set of dimensions may look simple from a larger one. A flat creature cannot imagine stepping over a wall. If a wall blocks the path on the surface, the creature must go around it or stop. But a three-dimensional being can simply lift a finger over the wall and touch the other side. To the flat creature, the wall is complete. To us, it is only a boundary on a surface. This difference between local experience and higher dimensional access is one reason extra dimensions appear so often in imaginative science. They suggest that some limits may be limits of viewpoint, not limits of reality itself. But again, physics moves carefully. It does not say, because we can imagine this, therefore it exists. The flat world analogy is not proof of a fifth dimension. It is a teaching tool. It shows that hidden directions are logically possible and that beings can be unaware of dimensions beyond their direct movement. It prepares the mind to consider the idea without immediately rejecting it as nonsense. That is all an analogy should do. If it does more, it starts wearing a hat too large for its head. Another useful example is the surface of Earth. To a person standing in a field, Earth looks flat. The horizon seems straight. The ground beneath your feet does not feel like the surface of a sphere. For everyday purposes, treating the ground as flat works well. You can build a house, walk to a shop, or set up a picnic without calculating the curvature of the planet. But over larger distances, the curvature matters. Ships disappear below the horizon. Airplanes follow curved routes. Satellites orbit. The flat picture is locally useful, but globally incomplete. This matters because extra dimensions might be hidden in a similar spirit, though in a much deeper way. A description can work very well at one scale and still miss structure at another scale. Our three-dimensional experience may be perfectly accurate for ordinary life, just as a flat map can be accurate enough for finding the nearest bakery. But when physics looks at very small distances, very high energies, or the early universe, the simple picture may need to be expanded. The fact that three-dimensional space works well for arranging furniture does not prove it is the full geometry of nature. Higher space also causes trouble because it breaks our usual idea of inside and outside. In 3 dimensions, a closed box has an inside and an outside. A locked room keeps things contained because the walls surround the space. But in 2 dimensions, a flat creature could be trapped inside a circle drawn on its plane. The circle would be a complete boundary for that creature. It could not cross the line without passing through it. Yet a 3-dimensional being could reach over the line and touch the inside without breaking it. The boundary that seems absolute within the plane is not absolute from above. Now apply that carefully to us. We understand closed surfaces in 3 dimensions. A sphere can enclose a volume. A sealed room can contain air. But a being with access to a higher spatial dimension might see our enclosures differently. What is sealed to us might not be sealed from the higher perspective. This is not something we can use practically because we do not have access to that direction. But it shows how our ideas of containment, separation, and distance depend on the dimensional structure we inhabit. This is why higher dimensions are not just about adding more space. They change relationships. They change what counts as near or far. In a flat world, 2 points separated by a long path on the surface might be close through the 3rd dimension if the surface is folded. Imagine a sheet of paper with 2 dots far apart. On the paper, an ant must crawl a long way from one dot to the other. But if the paper is folded so the dots nearly touch, a creature moving through 3-dimensional space sees them as close. This is often used to introduce ideas like wormholes, though those belong to another part of physics. The basic point is simpler. Distance depends on the space you're allowed to move through. If our universe has a hidden dimension, then what appears distant or separate in ordinary space might have deeper relationships in the larger geometry. This does not mean we can jump across the cosmos by thinking very hard about folded paper. That would be convenient, but it is not how physics works. It means that the structure behind distance may be richer than our direct experience suggests. The familiar map may not show every path because some paths may not be available to ordinary matter or may require conditions far beyond anything we can create. There is another difficulty. We often imagine dimensions as places, but a dimension is not quite a place. The surface of a table is a place. The room around you is a place, but length is not a place by itself. Width is not a separate world beside length. Height is not a hidden kingdom floating above the others. They are directions within the same space. A 5th dimension, if physical, would not necessarily be another universe next door. It would be another direction or degree of freedom in the structure of reality. This difference matters because popular language can make extra dimensions sound like mystical destinations when physics usually means something more precise and less theatrical. The flat world analogy helps with this too. Height is not a separate universe from the flat surface. It is a direction that includes the surface as part of a larger space. The flat creatures do not experience height, but height is not elsewhere in the usual sense. It is right there at every point of their surface, unavailable to them because their world is confined. A 5th dimension might be similar. It could be present at every point in our space, not far away in the sky, but hidden because we cannot move along it, or because it is too small to detect directly. This is a strange kind of closeness. We're used to hidden things being behind doors, under floors, inside boxes, or beyond horizons. But a hidden dimension could be hidden without being behind anything. It could be part of the structure of each point. This is difficult to picture, but the garden hose example from earlier helps. From far away, the hose appears like a simple line. Up close, there is a small circular direction around it. That extra direction is not located somewhere else along the hose. It exists at every point along the hose. If an extra dimension is curled up in space, it might be like that, present everywhere, but too tiny for large objects to explore. Flatland stories also show how science might discover a hidden dimension indirectly. Suppose the flat creatures noticed that some force in their world behaved oddly. Perhaps it grew weaker faster than expected. Perhaps energy seemed to disappear and return. Perhaps particles appeared with patterns that made no sense in 2 dimensions alone. A brilliant flat physicist might propose that their world is part of a larger space. Other flat citizens might complain that this sounds too strange, especially before breakfast. But if the theory made predictions and those predictions were confirmed, the idea would become science, even if no one could picture height directly. This is similar to how physicists think about extra dimensions today. They do not expect to see a 5th dimension with a camera. They search for effects. Does gravity behave differently at tiny distances? Do particle collisions produce signs that energy is moved into a hidden direction? Are there patterns in the masses or interactions of particles that suggest compact extra geometry? Are there features in cosmology that could hint at a larger dimensional structure? These are difficult questions, and so far the evidence has not given a clear yes. But the method is grounded. Hidden does not mean unreachable to reason. It means the clues may be indirect. One of the most important lessons from flat worlds is humility. A flat creature could become an expert in its surface. It could measure distances, predict motion, build machines, write textbooks, and still miss the larger space. Its knowledge would be real, not false. It would simply be incomplete. That is a useful model for us. Our physics is not foolish because it begins in 3 dimensions. It has worked astonishingly well. It sends spacecraft across the solar system, explains atoms, predicts light, and makes technology possible. But success at one level does not guarantee completeness at every level. The universe may still have hidden structure. There is also a lesson about language. The flat creature cannot describe height in familiar terms because all its words come from the surface. It may borrow words like outside, above, or through, but those words do not fully fit. We have the same problem with the 5th dimension. We say beyond, outside, curled, hidden, or higher, but each word is borrowed from ordinary 3-dimensional experience. None of them is perfect. Higher does not mean up, hidden does not mean behind a curtain, curled does not mean physically rolled like a carpet in the usual sense. These words are handles, and sometimes they wobble. That is why patience matters. Higher dimensional thinking is not about forcing the mind to see what it cannot see. It is about learning to reason with limitations. We can use lower dimensional examples. We can study shadows and slices. We can follow mathematics. We can ask what consequences would appear in our world. We can stay honest about the difference between helpful images and physical proof. The subject becomes less confusing when we stop demanding a perfect picture and start accepting partial tools. Even in ordinary life, we already understand partial views. A medical scan shows slices of a body, not the whole body at once. A photograph shows one angle of a person, not every side. A shadow tells us something about an object, but not everything. A footprint tells us something passed by, though not the full story of where it came from. Much of science works this way. We rarely get the whole thing at once. We gather traces and build the larger picture carefully. If a 5th dimension exists, our universe may be giving us traces rather than a direct view. Gravity might be one such trace. Particle behavior might be another. The structure of space-time might carry hints. Or perhaps the clues are absent because the dimension does not exist, or because it is hidden at scales far beyond current experiments. Both outcomes are valuable. If we find evidence, our picture of reality expands. If we do not, we learn which beautiful ideas nature chose not to use, and physics becomes sharper. The trouble with higher space, then, is not only that we cannot picture it. The deeper trouble is that our instincts keep trying to reduce it to something familiar. We turn it into a place, a tunnel, a realm, a secret room. Those images can help at first, but they can also mislead. The real scientific idea is more careful. A 5th dimension would be an additional part of the geometry or description of nature, possibly compact, possibly large but inaccessible, possibly linked to forces and still unconfirmed. It is not a shortcut to fantasy. It is a question about the structure of space itself. And yet, even with all the caution, The idea remains deeply interesting because once you understand the flat world, you see how easily a complete universe can be only a surface from a larger point of view. You see how a creature can live its whole life inside a limited space and never suspect the extra direction beside it. You see how shadows can hint at forms that cannot be seen directly. You see how slices can appear mysterious until the larger object is known. The familiar world becomes less final, not less real. More like a page in a book whose binding we cannot yet see. So when we return to our own room, our own sky, our own three directions, they may feel slightly different. Forward and backward still work. Left and right still work. Up and down still work. Nothing has vanished. The chair has not become uncertain about its duties. But behind the stability of ordinary space, we can now hold a careful question. Could everything we see be a slice of a larger geometry? Could the forces we measure be shadows of deeper structure? Could the universe, like the flat world, be complete to its inhabitants while still being embedded in something wider? These questions do not yet tell us what the fifth dimension is. They only prepare us to understand why the idea is not meaningless. To go further, we have to return to the moment when space itself stopped being a passive background. We have to move from flat worlds and shadows into Einstein's great change, where space and time were woven together and gravity became geometry. Because once space-time became flexible, curved, and physical, the thought of another hidden direction began to look less like a fairy tale and more like the next strange door in a house physics was already exploring. By the time we reach Einstein, space has already become a little less ordinary. We have imagined flat worlds, shadows, slices, and creatures who cannot see the larger room around them. We've learned that a dimension is not always something the eye can picture, but a kind of freedom, a way for reality to be described. Now, the story takes a deeper turn. Because before physicists could seriously wonder about a fifth dimension, they first had to realize something astonishing about the dimensions we already know. Space and time were not separate. They were not a stage and a clock. They were part of one flexible structure. That may sound familiar now because relativity has become one of those famous ideas that floats around culture like a grand scientific cloud. People know that Einstein changed time. They know that clocks can slow down, that gravity can bend light, that black holes are strange, and that someone somewhere will eventually use the phrase "everything is relative" during an argument where it does not quite belong. But beneath the familiar fame is a very careful shift in how reality is understood. Einstein did not simply add a few surprising effects to an otherwise normal universe. He changed the meaning of space itself. Before Einstein, the old picture was beautifully simple. Space was the container. Time was the clock. Objects moved inside space as time passed. A planet crossed the heavens. A stone fell to Earth. A train moved along a track. In this older view, space was like the floor of an enormous theater, and time was like an invisible conductor keeping the rhythm steady for everyone. No matter where you were, no matter how you moved, the great cosmic clock ticked on in the same way. It felt sensible. It matched ordinary life. If you and a friend meet for tea at 4 in the afternoon, neither of you expects the universe to disagree about what 4 in the afternoon means, unless one of you is very late and looking for a creative excuse. Newton had built an extraordinary system on this idea. His laws of motion and gravity worked so well that they seemed almost final. They explained falling apples, orbiting moons, tides, comets, cannonballs, and much of the machinery of the world. For centuries, Newtonian physics gave humanity a universe that behaved like a precise clockwork mechanism. It was elegant, reliable, and powerful. In the slow and moderate world of everyday speeds and familiar gravity, it still works so well that engineers, pilots, builders, and astronomers can use it with great success. If you drop a biscuit, Newton is more than enough to tell you where it is going, though perhaps not why you were holding it over the carpet. But light brought trouble. Light refused to behave like ordinary things. If you throw a ball while running, the ball's speed depends on your motion. If you move towards something, you expect to meet it faster. This is common sense. Yet, experiments and the developing theory of electromagnetism suggested that light had a fixed speed, one that did not change depending on the motion of the observer. That was deeply strange. It meant that something in the old picture had to give way. If the speed of light stayed the same for everyone, then space and time could not remain absolute in the old Newtonian sense. Einstein's great move was to take that strange constancy seriously. Instead of treating it as an inconvenience, he built a new picture around it. In Special Relativity, published in the early 20th century, he showed that measurements of time and space depend on the motion of the observer. Two observers moving relative to each other can disagree about how much time passed or how long something is. Yet both can be correct within their own frame of reference. The laws of physics remain consistent, but space and time adjust themselves in a way no one had expected. This is where time stops being the universal river. A moving clock can tick more slowly compared with a clock at rest. A moving object can be measured as shorter along its direction of motion. Events that seem simultaneous to one observer may not be simultaneous to another. These effects are not illusions in the ordinary sense. They are not mistakes made by bad watches or sleepy scientists. They are part of how the universe preserves the same speed of light for all observers. Space and time bend their measurements around that rule. For daily life, this is hidden because we move slowly compared with light. Walking to the kitchen does not noticeably change the flow of your time, even if the journey feels long when you're tired. A car ride does not make you return dramatically younger than the person who stayed at home. The effects are tiny at ordinary speeds, but they are real. They have been measured with precise clocks, fast particles, and modern technology. The universe is not built from absolute space and absolute time. It is built from something deeper, something in which space and time are linked. That deeper thing came to be called space-time. It is not just space plus time in the casual sense. It is a unified structure in which events have positions not only in the three directions of space, but also in time. An event is not simply where something happens. It is where and when. The flash of lightning, the fall of a stone, the tick of a clock, the arrival of morning light through a curtain, all have places in space-time. This may sound like a small change in language, but it is a huge change in physics. It means that the universe is not made of things moving through space while time flows independently above them. It means the stage and the clock are woven together. One of the helpful ways to think about this is to imagine a book. Each page is like a moment, a whole arrangement of space at one time. The story is not found on one page alone, but in the relationship between pages. The motion of a character, the fall of rain, the change from evening to night, all require a sequence. Space-time is not exactly a book, but the comparison helps. It suggests that events are part of a larger structure, not just little happenings floating in a universal now. In relativity, there is no single cosmic present shared by everyone in the same simple way. Different observers can slice space-time into past, present, and future differently depending on their motion. This is a strange idea, but it opened a door. If time could be treated as part of geometry, then geometry was no longer just about shapes drawn in space. Geometry became part of physical reality. The structure of space-time determined how observers measured the world. And then Einstein went even further. Special relativity dealt with motion at steady speeds, but the universe also has gravity, and gravity was the great force Newton had described so successfully. Einstein wanted to understand gravity in the new language of space-time. The result was general relativity, completed about a decade later. This theory changed gravity from a force acting across space into the curvature of space-time itself. Massive objects do not simply pull on other objects in the old sense. They shape the space-time around them, and other objects move along the paths that this curved space-time allows. The sun curves space-time, and Earth follows a path through that curvature. Earth curves space-time, and the moon follows its path. A falling apple is not merely being tugged downward. It is following the geometry of space-time near Earth, though it would probably not find that explanation comforting on the way to the ground. The usual image is a heavy ball resting on a stretched sheet making a dip, with smaller balls rolling around it. This image is useful but also imperfect. A real sheet is a two-dimensional surface bending into a third dimension, while space-time curvature does not need an outside space. In the same way, the universe is not literally sitting on a rubber sheet, and gravity is not caused by some invisible cosmic mattress. Still, The image gives a feeling for the idea that mass changes geometry and geometry guides motion. Matter tells space-time how to curve. Curved space-time tells matter how to move. This was one of the greatest conceptual shifts in science. Space and time were no longer passive. They were active. They responded to matter and energy. They carried gravitational waves. They could stretch, curve, and form extreme regions where ordinary intuition breaks down. Near a very massive object, time itself runs differently. A clock closer to a strong gravitational field ticks more slowly than one farther away. This is not a metaphor. It is measured and used in technology. Satellites above Earth must account for the way time passes differently in orbit compared with the surface. Without those corrections, navigation systems would slowly lose accuracy, and your map might guide you somewhere quite unexpected, perhaps into a lake, which would be an unfair price to pay for ignoring relativity. General relativity made the universe feel both more elegant and more unsettling. It united gravity with geometry, which is a beautiful idea, but it also made space and time dynamic. They were no longer fixed background furniture. They were more like the fabric of the world itself, shaped by what it contains. And once physicists learned to think this way, the question of extra dimensions became more natural. If gravity is geometry, then perhaps other forces might also be geometry in a larger space. If the shape of space-time explains gravity, perhaps an added dimension could explain something else. This is the doorway to something deeper. Not because Einstein himself proved a fifth dimension, but because his work made it reasonable to think that the laws of nature might come from the structure of space and time. Before relativity, adding another dimension might have seemed like mathematical decoration. After relativity, dimensions had physical power. A change in geometry could mean a change in gravity. A curve in space-time could guide planets. A hidden direction, if real, might affect forces, particles, or the behavior of the universe itself. To see why this mattered, think again about shadows. In a flat world, a curved surface may reveal itself through strange motion. A creature living on that surface might think objects are being pulled by invisible forces when actually they are following the shape of the surface. General relativity says something similar about gravity. What looks like a force can be understood as geometry. That idea naturally invites a further question. Could some other force also be a sign of hidden geometry? Could electromagnetism, for example, come from the shape of an extra dimension? This was one of the bold dreams that followed Einstein. The timing was important. In the early 20th century, physics was discovering two revolutions at once. Relativity was changing the large-scale structure of space, time, and gravity. Quantum theory was changing the small-scale behavior of matter, light, and atoms. The old mechanical universe was opening at both ends. On the cosmic scale, space-time curved. On the atomic scale, particles behaved like waves and probabilities. Reality was becoming less like a machine with tiny solid parts and more like a set of deep patterns, fields, and relationships. In that atmosphere, the idea of another dimension did not feel like pure fantasy. It felt like one more attempt to find the hidden pattern. Einstein himself spent much of his later life searching for a unified theory, a way to bring gravity and electromagnetism into one coherent framework. He did not succeed in the final sense, but the desire was powerful. Physics had already shown that electricity and magnetism were connected aspects of electromagnetism. It was tempting to wonder whether gravity and electromagnetism might also be connected, if only we could look at them correctly. A fifth dimension offered one possible way to do that. It suggested that what appears as electromagnetism in our four-dimensional space-time might be related to the geometry of a five-dimensional world. This is a remarkable thought. It means that a force might not be a separate ingredient at all. It might be a shadow of shape. Just as gravity became the curvature of space-time, perhaps another force could be curvature or motion involving an extra direction. From our limited view, we would see fields, charges, and forces. From the higher dimensional view, those might be aspects of a larger geometric structure. This is the kind of idea that makes physics feel almost like detective work in a dark house. You find footprints in one room, a draft in another, a door that looks sealed, and slowly you begin to suspect that the building has another floor. But it's important not to rush. Einstein's theories are tested and confirmed with great precision. The fifth dimension is not confirmed in the same way. General relativity opened the conceptual door, but walking through it requires more than elegance. A hidden dimension must make predictions that match nature. It must explain something real. It must survive experiment. Many versions of extra-dimensional theories have been proposed, refined, challenged, and constrained by evidence. Some remain possible. Others have been ruled out or made less likely. This is the normal life of scientific ideas. They do not float safely above the world. They are tested against it. Still, the reason Einstein matters in this story is that he changed the status of geometry. Before him, geometry might have seemed like a human way of describing shapes. After him, geometry became an actor in the universe. The shape of space-time was not just a description of gravity. It was gravity. That is a profound doorway. Once geometry can act, hidden geometry becomes a serious possibility. If there are extra dimensions, their shape and size would not be idle details. They could determine the strengths of forces, the types of particles that exist, or the way the universe evolved. This is where the word hidden becomes especially interesting. In relativity, space-time can be curved even when you do not feel it directly. You do not feel Earth moving around the sun in the same way you feel a breeze on your face. You do not see space-time curvature with your eyes. You infer it from motion, from clocks, from light bending, from waves passing through detectors. In the same way, a fifth dimension would likely be known through effects, not direct sight. The hidden is not beyond science just because it is not visible. Much of science is the art of making the invisible accountable. Einstein also taught physics to distrust the obvious. Time feels universal. It is not. Space feels fixed. It is not. Gravity feels like a pull. At a deeper level, it is geometry. These lessons loosen the grip of common sense. They do not tell us to abandon reason. They tell us to refine it. Common sense is built for slow speeds, weak gravity, and objects large enough to touch. The universe is larger than that. When we study light, black holes, atoms, and the early cosmos, we must be willing to let familiar ideas change shape. A fifth dimension asks for that same willingness. It asks us to imagine that the space we know may be a lower dimensional part of a larger structure, not because ordinary space is wrong, but because it may not be complete. This is very similar to how Newtonian physics is not wrong in everyday life. It is a limiting picture, a reliable approximation. Relativity did not make falling apples stop obeying Newton in the kitchen. It showed that Newton's picture is part of a broader one. Perhaps our familiar space-time is also part of a broader picture, one that includes hidden dimensions at scales or energies beyond daily life. The difference is that relativity has been tested in countless ways while the fifth dimension remains a question. That distinction should stay clear, but questions can be powerful before they become answers. The idea of space-time itself was once difficult and strange. The bending of light by gravity was once a bold prediction. Gravitational waves were once a consequence waiting for detection. Physics often lives for a long time with ideas that are mathematically compelling before experiments become sensitive enough to confirm or deny them. The fifth dimension belongs to this patient territory. There is another quiet connection between relativity and extra dimensions. General relativity describes a smooth space-time, while quantum physics describes a restless world of uncertainty and fields. When physicists try to bring these together, the old four-dimensional picture becomes strained. At extremely tiny scales, space-time may not remain smooth. It may have a kind of hidden structure, perhaps involving extra dimensions, perhaps something even stranger. The search for quantum gravity is partly a search for the deeper material from which space-time itself is made, if made is even the right word. In that search, the fifth dimension is one possible clue. So Einstein's space-time is not the final room in the story. It is the room where a new door appears. We enter with ordinary space and time. We leave with a flexible four-dimensional universe where gravity is geometry. Once that happens, it becomes easier to imagine that geometry might have more to say. Maybe a fifth dimension is curled tightly at every point. Maybe our universe is a surface inside a larger space. Maybe gravity reaches into places matter cannot. Maybe the forces we treat as separate are different views of a hidden shape. Or maybe the universe stops at four dimensions and the fifth is only a beautiful mathematical dream. Each possibility remains part of the investigation. For now, the important thing is the change in attitude. Space is no longer empty nothingness. Time is no longer a universal ticking. Gravity is no longer simply a mysterious pull across distance. The fabric of reality has become something that can bend, stretch, ripple, and guide motion. It has become physical enough that asking about its deeper dimensions no longer sounds like idle fantasy. It sounds like the next question a curious mind might ask after learning that the floor of the universe was never as flat or firm as it seemed. And so from Einstein, the story begins to lean toward the strange dream that came next. If four-dimensional spacetime can explain gravity, perhaps five-dimensional spacetime could explain more. Perhaps the extra direction is not visible because it is curled away, tiny and silent. Perhaps electromagnetism, the force of light, magnets, and electric charge could be connected to the shape of that hidden direction. This idea would lead to one of the most elegant and unusual attempts in physics, a theory that reached beyond Einstein's spacetime and imagined the universe with one more secret fold. After Einstein changed the meaning of gravity, space no longer felt like an empty stage. It had become something with shape, something that could bend around stars, stretch across the universe, and carry the quiet instruction for how matter should move. That was already a deep change, the kind of change that makes ordinary rooms feel just a little more mysterious. But for some physicists, it also raised a tempting question. If gravity could be understood as geometry, could other forces be geometry too? Could the universe be simpler than it looked? Not because it had fewer parts, but because some of those parts were actually different faces of one hidden structure. This question led to one of the strangest and most elegant ideas in early modern physics. It began with a German mathematician named Theodor Kaluza who looked at Einstein's theory and wondered what would happen if spacetime had one more dimension. Not just the three dimensions of space and the one dimension of time, but an additional direction beyond them, a fifth dimension, a hidden extension of the universe that no one could see, touch, or move through in daily life. At first, this may sound like adding an extra room to a house because the furniture is not arranged properly. But Kaluza was not adding the fifth dimension for decoration. He was trying to see whether the mathematics of gravity, when lifted into a five-dimensional framework, might naturally include another force, and not just any force. Electromagnetism, the force behind light, electric charge, magnets, lightning, radio waves, chemistry, and the tiny electrical activity that lets your brain follow this sentence while hopefully becoming just sleepy enough to relax. Electromagnetism was already one of the great successes of physics. It had been beautifully described in the 19th century when electricity and magnetism were shown to be two connected aspects of one field. Before that, electricity and magnetism had seemed like separate phenomena. One made sparks and currents. The other made compass needles turn and magnets cling to refrigerator doors with surprising emotional commitment. But the work of physicists showed that they belonged together. Changing electric fields could create magnetic fields, and changing magnetic fields could create electric fields. Light itself turned out to be an electromagnetic wave, so by the time Kaluza began thinking, physics already had a powerful example of unification. Electricity and magnetism were not two unrelated forces. They were one deeper thing seen in different ways. Einstein had then shown that gravity could be understood through the geometry of spacetime. To Kaluza, a new possibility opened. Maybe gravity and electromagnetism could also be unified, not by forcing them together, but by placing them in a larger geometry where their connection became natural. The idea was bold. Suppose the universe has 5 dimensions instead of 4. In that larger spacetime, gravity would be described by the shape of the 5-dimensional geometry. But when seen from our ordinary 4-dimensional point of view, part of that geometry would look like gravity and another part would look like electromagnetism. In other words, electromagnetism might be a shadow of gravity in a higher dimensional world. What seems like an electric or magnetic force to us might be in the deeper picture a sign of curved geometry involving the hidden dimension. That is a beautiful thought. It suggests that a force might be nothing more mysterious than the shape of space we cannot fully see. In our familiar world, a charged particle feels an electromagnetic field. It accelerates, bends, radiates, and interacts. In Kaluza's higher dimensional picture, some of that behavior might come from the particle moving through or being influenced by the geometry of a fifth direction. Just as general relativity turned gravitational force into curved spacetime, Kaluza hoped that electromagnetism could be turned into hidden geometry. There is a certain quiet elegance to this. It is like discovering that two different melodies played in different rooms are actually parts of the same song, but one of the instruments has been hidden behind a wall. From where we stand, gravity and electromagnetism behave very differently. Gravity pulls on everything with mass and energy. Electromagnetism acts on electric charge and can both attract and repel. Gravity shapes planets, stars, and galaxies. Electromagnetism shapes atoms, chemistry, light, and nearly everything we experience as touch and material structure. They do not look like twins, but perhaps Kaluza wondered they might be cousins in a larger family of geometry. When Kaluza sent his idea to Einstein, Einstein was intrigued. That alone says something. Einstein was not easily impressed by every new mathematical adventure, and physics has always had plenty of those. But Kaluza's proposal had a kind of surprising power. By extending general relativity into 5 dimensions, certain pieces of the equation seemed to resemble the equations of electromagnetism. It was as if the hidden direction had brought electric and magnetic fields along with it, tucked inside the larger structure. A 5th dimension, once introduced, did not sit quietly in the corner. It began to do real work, but there was an immediate problem. If there is a 5th dimension, where is it? Why do we not notice it? Why can you not move into it? Why does your hand stop at forward, backward, left, right, up and down instead of casually drifting along another direction while you're trying to find your slippers? A theory that adds a dimension must explain why that dimension is hidden. Otherwise, the idea feels incomplete. Kaluza had assumed that nothing changed along the 5th dimension, almost as if the universe had that direction but did not vary through it. This helped the mathematics, but it left the physical picture unclear. A few years later, Oscar Klein offered the missing image. He suggested that the 5th dimension might be curled up, not stretched out like the familiar dimensions of space, but looped into a tiny circle at every point, so tiny that ordinary objects could never move through it in any noticeable way. The dimension would be real but compact, present everywhere yet hidden because it was far too small for human-scale experience. This was the strange dream of a curled-up dimension. The garden hose analogy helps again, even if the real physics is much smaller and much more subtle. Imagine looking at a long hose from far away. It seems like a simple line. Something moving along it appears to have only one direction available, forward or backward along the hose. But if you were tiny enough and close enough, you would see that the hose has another direction too. You could move around its circular surface. The extra direction was there all along. It was simply too small to see from a distance. To a large observer, the hose looked one-dimensional. To a tiny observer, it was more than that. Klein imagined that the 5th dimension might be like the small circular direction around the hose. At every point in ordinary space, there could be a tiny loop of additional space curled so tightly that we never notice it. We move through the large dimensions. Particles, however, might in some way feel the hidden circle. Its size and shape could influence the properties of matter and forces. The hidden dimension would not be far away. It would be closer than close, attached to every point in the universe, but folded down to a scale beyond ordinary reach. This is one of those ideas that sounds almost impossible at first, but becomes more understandable when we think about scale. Human beings live in the middle scale of the universe. We are much larger than atoms and much smaller than galaxies. Our senses are tuned to chairs, trees, faces, food, weather, and the occasional suspicious noise from another room. We do not directly perceive the microscopic structure of matter. We do not see the graininess of a photograph from far away. We do not notice the fibers in cloth until we look closely. So perhaps space itself could have fine structure too, hidden not by distance but by smallness. The idea of compact dimensions changed the way physicists could think about extra space. A 5th dimension no longer had to be a huge direction waiting visibly beside us. It could be real and invisible at the same time. It could be part of the deep architecture of the universe without disturbing daily life. This was important because it answered the most obvious objection. If the 5th dimension exists, why does the world seem 3-dimensional in space? Because the extra direction may be curled so tightly that large objects cannot explore it. Just as a person walking along a road does not notice every tiny crack in the pavement unless they kneel down. Ordinary matter may pass through familiar space without detecting the hidden loop at every point. Kaluza and Klein's idea did not become the final theory of nature. It was too simple in some ways, and physics soon became more complicated. Quantum mechanics rose with all its strangeness. New particles were discovered. The strong and weak nuclear forces entered the story. The universe turned out to have more ingredients than gravity and electromagnetism alone. Kaluza and Klein had aimed to unify two forces, but nature revealed a larger cast. Still, their idea did not disappear. It became a seed. It showed that extra dimensions could be physically meaningful, not just imaginary. It showed that geometry in a hidden direction could appear as a force in the visible world. That seed would later grow into many parts of modern theoretical physics. In attempts to unify all forces, especially in string theory and related ideas, extra dimensions appear again and again, not just one extra dimension, but several. These dimensions are often imagined as compact, curled into intricate shapes too small to see directly. The shape of the hidden dimensions could determine the kinds of particles and forces we observe, a bit like the shape of a musical instrument determines the notes it can play. A violin string, a flute, and a drum all involve vibration, but their shapes make different sounds. In a similar spirit, the geometry of hidden dimensions might shape the physical music of the universe. This does not mean that string theory or extra dimensions have been proven. They have not. But the Kaluza and Klein idea remains historically important because it taught physicists a new language. It suggested that what we call forces might arise from geometry. It suggested that small hidden dimensions could exist without contradicting ordinary experience. It suggested that the visible universe might be only a lower dimensional expression of a richer structure. Even if the original version was incomplete, its imagination was powerful enough to influence generations. There is also something deeply human about the story. Kaluza was not working with a giant machine or a telescope staring into the early universe. He was working with an idea. He asked what would happen if the mathematics of Einstein's spacetime were allowed one more direction. Sometimes physics advances not by looking farther outward, but by changing the rules of the question. It is like turning a key in a lock no one else noticed was there. The room may not open fully, but the sound of the lock moving tells you something. And Klein added the part that made the idea physically plausible. A hidden dimension could be curled up. That phrase has a gentle quality, almost like the universe has tucked part of itself away for the night. But the concept is sharp. If a dimension forms a tiny closed loop, motion along it would be limited. At large scales, the loop disappears from view. At small scales, it could affect quantum behavior. This gives physicists a way to hide extra structure without removing it. The universe may be large in three directions and tiny in another. It may be spacious and folded at the same time. One of the strange consequences of a curled dimension is that motion around it could be restricted in special ways. A particle moving around a tiny loop cannot have just any kind of motion. It must fit the loop. This can lead to discrete patterns, rather like a guitar string can only vibrate in certain allowed ways. In some later theories, these allowed patterns can appear to us as different particle properties. We do not need to go into the mathematics to appreciate the idea. The hidden shape limits what can happen, and those limits show up as the physical features we measure. Geometry becomes law. This is a remarkable reversal of ordinary thinking. We usually imagine laws as rules imposed on objects moving through space. But in geometric physics, the shape of space itself can produce the rules. The path of a planet follows curved space-time. The behavior of a particle may reflect hidden structure. The force is not simply placed into the universe from outside. It emerges from how the universe is built. This is why extra dimensions have such lasting appeal. They promise not merely more space, but deeper explanation. Still, there is a quiet danger in beauty. A theory can be elegant and still not describe nature. Kaluza and Klein's idea was beautiful, but beauty is not evidence. The universe has the final say, and it speaks through measurement. If compact dimensions exist, they may leave traces. They might affect particle masses. They might create heavier versions of known particles at high energies. They might modify gravity at very small distances. Physicists have searched for such signs in many ways, from particle accelerators to delicate tests of gravity. So far, no unmistakable evidence has appeared. The curled dimension remains a possibility, not a discovery, but even the absence of evidence teaches something. Experiments place limits on how large extra dimensions could be, how they might behave, and what kinds of theories remain possible. Science does not only confirm ideas, it narrows them, disciplines them, and sometimes gently asks them to leave the room. The fifth dimension survives only if it can stay consistent with what we observe. That is what keeps the idea scientific. It can be imagined, but it must also be constrained. For a calm listener drifting towards sleep, it may be enough to hold the image softly. At every point in space, perhaps there is a tiny curled direction, like a hidden circle too small to enter. The room around you would not look different, the walls would not shimmer, your blanket would not suddenly reveal a secret geometry, although that would certainly make laundry more interesting. Everything would remain ordinary at human scale, yet beneath that ordinary surface, the universe might carry a fine curled structure, a small hidden freedom woven into every location. This is one of the themes that makes physics both humbling and comforting. The familiar world does not vanish when deeper layers are found. It becomes richer. Learning that matter is made of atoms does not make a wooden table less real. Learning that gravity is curved space-time does not make falling less effective. Learning that space might have hidden dimensions would not make the room unreal. It would mean that the room is part of a deeper geometry, just as a calm ocean surface may hide currents below. Kaluza and Klein gave physics a way to imagine that hidden depth. They took Einstein's space-time and asked whether one more dimension could make two great forces look connected. They gave the fifth dimension a hiding place by curling it into a tiny loop. They showed that the unseen might not be distant or mystical, but compact and geometric. Their idea did not solve everything, but it opened a path, and many later theories would walk along that path, asking whether all the particles and forces of nature might be shaped by dimensions too small for us to see. As we move forward from this strange and elegant dream, the hidden dimension begins to change shape again. It is no longer only a tiny curled circle at every point. In later ideas, our entire universe may be imagined as a kind of surface, a vast cosmic sheet. While a larger space extends beyond it, matter may be trapped on that sheet. While gravity may wander more freely, the fifth dimension becomes not just a secret loop, but a possible surrounding space, one that could explain why gravity behaves so differently from the forces that hold atoms and light together. The idea of a curled-up dimension is small and quiet, tucked into every point of space like a secret loop too tiny for ordinary life to notice. But as physics moved forward, another picture began to grow beside it. Maybe the hidden dimension is not only a tiny circle folded away beyond reach. Maybe our whole universe is like a vast surface inside a larger space. Maybe everything we see, every star, every galaxy, every atom, every sleepy cup of tea cooling beside a bed, belongs to a kind of cosmic sheet. And maybe beyond that sheet, in a direction we cannot enter, there is more space. This is where the word brain enters the story. It sounds a bit like someone began saying membrane and got tired halfway through, which is not entirely wrong. In physics, a brain is a kind of extended object. A membrane is like a two-dimensional surface, something with length and width. A brain is the more general idea. It can have many dimensions. A universe in some theories may be imagined as a three-dimensional brain, meaning a place with the three spatial directions we know, embedded inside a larger, higher-dimensional space. That larger space is often called the bulk, which is a wonderfully plain word for something so strange. It sounds less like the hidden home of higher reality and more like a storage cupboard. But physicists are allowed a little understatement now and then. The brain idea gives us a different way to think about hidden dimensions. In the curled-up picture, the extra dimension is very small. In the brain picture, the extra dimension might be large, perhaps even vast, but ordinary matter cannot move through it. We are not unable to notice it only because it is tiny. We are unable to enter it because the particles and forces that make us are stuck to the brain. It is as if the universe we know is a surface, and everything made of familiar matter is confined to that surface, not by walls, but by the rules of physics themselves. To make this easier, return for a moment to the flat world. Imagine flat creatures living on a sheet. They can move forward and backward, left and right, but not upward. Now suppose the sheet is floating inside a much larger three-dimensional room. The creatures may never know the room exists, not because the room is small, but because they cannot leave the sheet. Their bodies, their houses, their light, their measuring tools all belong to the surface. The larger space is not far away in the ordinary surface directions. It is right beside them in a direction they cannot access. If they studied their world carefully enough, they might begin to suspect something beyond it, but they would not simply walk there. In brain theories, we may be in a similar position. Our particles could be confined to a three-dimensional brain inside a higher dimensional bulk. This does not mean the universe is literally a thin piece of paper floating in a dark room. Analogies always begin to wobble if we lean on them too hard. It means that the mathematics allows our familiar world to behave like a lower dimensional surface inside a higher dimensional structure. The visible universe could be like a slice, not because it is an illusion, but because the matter composing us cannot travel off that slice. At first, this may feel almost claustrophobic. Are we trapped on a cosmic sheet? But it would not feel like a trap from the inside. A fish does not experience water as a prison. A person walking on Earth does not feel confined to the surface in any deep cosmic sense. Even though most daily life happens along the ground, if all known particles and forces move only within our brain, then the brain is our universe for every ordinary purpose. It contains our skies, oceans, mountains, bodies, memories, and the small domestic mystery of why charging cables always become tangled. Nothing in daily experience would announce that a larger bulk exists. The reason physicists became interested in brains has a lot to do with gravity. Gravity is familiar, but it is also odd. It is the force we notice earliest as children, usually when we drop something, fall over, or discover that cups do not float obediently in midair. Yet, compared with the other fundamental forces, gravity is astonishingly weak. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. That is worth pausing over. The planet beneath you, with all its rock, metal, ocean, and atmosphere, is pulling downward, and a tiny magnet can win. Gravity shapes galaxies, but at the scale of particles, it is feeble. This weakness is one of the puzzles that extra dimensions have tried to address. In some brain models, the forces of particle physics, such as electromagnetism and the nuclear forces, are confined to our brain. They cannot spread into the higher dimensional bulk. Gravity, however, may be different because gravity is tied to the geometry of space-time itself. It may be able to move through the larger space beyond our brain. If gravity spreads out into hidden dimensions while other forces remain stuck with us, then gravity would appear weaker in our universe. Not because gravity is truly weak at its source, but because some of its influence leaks into directions we cannot see. This is a powerful image. Imagine water poured onto a flat surface. If it can only spread across the surface, it remains concentrated in that area. But if it can also seep downward into hidden layers beneath, the surface effect becomes weaker. Or imagine sound in a room. If sound is trapped in one room, it seems loud. If the walls allow it to leak into hallways and chambers beyond, it becomes softer. In a similar spirit, gravity might seem weak because it is not confined to our visible world. It may be diluted through the bulk. Of course, gravity does not literally leak like water through a ceiling, and the universe is not a badly maintained apartment. The word leak is only a helpful way to picture a mathematical idea. The real question is whether gravity behaves as if it has access to extra dimensions. If it does, then at very small distances where hidden dimensions might become important, gravity might deviate from what we expect. Scientists have tested gravity at extremely small scales to look for such deviations. So far, no clear evidence of extra dimensions has appeared, but the search has placed important limits on what those dimensions could be like. The brain idea also grew from string theory, where the basic ingredients of nature are not point-like particles in the usual sense, but tiny vibrating strings. In that framework, brains appear naturally as objects on which open strings can end. This matters because particles and forces can be represented by different vibrational patterns of strings. Some strings may be tied to brains, while others, especially those connected with gravity, may move through the larger space. Again, the details are highly mathematical, but the broad image is this. The matter and forces we know may be anchored to our brain, while gravity may wander through a higher dimensional background. This gives gravity a special role. It may be our one messenger from the bulk. Light may be trapped on the brain. Electromagnetism may be trapped. the particles of our bodies may be trapped, but gravity, being a feature of geometry, may not be fully confined. If that is true, then gravity could carry clues about dimensions we cannot otherwise reach. It would be like hearing a faint echo through a wall and realizing there may be another room beyond it, even though no door is visible. This is one reason brain worlds are so intriguing. They offer a way to imagine hidden dimensions, not as remote fantasies, but as possible explanations for a real imbalance in physics. Gravity's weakness becomes not just a fact to accept, but a clue. Perhaps the force that holds planets in orbit and bends the paths of galaxies is also the only force quietly touching the larger space around our universe. That thought gives gravity an almost lonely character. It is everywhere, always present, always patient, and perhaps always partly elsewhere. Brain theories can also change how we think about the beginning of the universe. In the familiar Big Bang picture, the universe was once extremely hot and dense, then expanded and cooled over billions of years. In some higher dimensional ideas, the Big Bang might be related to events involving brains. Perhaps two brains moved in the bulk and collided. Perhaps our universe was heated and filled with matter by such a collision. This is speculative and not part of the confirmed standard picture, but it shows how extra dimensions can reshape even the largest questions. The beginning of everything we see might be connected to motion in a space we cannot see. There are also ideas in which other brains may exist beyond ours. If our universe is one brain in a larger bulk, there could be other brains elsewhere along the hidden dimension. These would not be parallel worlds in the simple storybook sense, with another version of you choosing a different breakfast. They would be separate physical surfaces, possibly with their own particles or forces, perhaps unreachable because ordinary matter cannot cross the bulk. Their existence is speculative, but the concept naturally arises in some models. A larger dimensional space may contain more than one lower dimensional universe. This can sound dramatic, and it is easy for imagination to run ahead. One pictures ghostly neighboring universes floating a hair's breadth away, invisible companions separated by a direction no hand can point toward. But physics must remain careful. There is no confirmed evidence that such neighboring brains exist. The value of the idea is not that it gives us a secret cosmic neighborhood to daydream about, though it certainly does that rather well. The value is that it gives physicists new ways to ask old questions. Why is gravity weak? How might quantum physics and gravity fit together? What was the early universe like? Are the constants of nature shaped by hidden geometry? The word thin in the phrase cosmic sheet can also be misleading. A universe would not feel thin to us. It contains three vast spatial directions and may extend over distances beyond imagination. Galaxies are separated by enormous gulfs. Light takes billions of years to cross the visible cosmos. If this is a sheet, it is not small in the directions we know. It is thin only in relation to a direction outside our experience. A sheet of paper can be wide and long while being thin in height. A brain could be vast in 3 dimensions and limited in the 5th. From inside, we experience the vastness, not the thinness. This helps explain why ordinary observation does not settle the question. Looking across the universe with telescopes tells us about distances within our brain. It does not automatically reveal whether there is a direction outside it. We may be like flat astronomers mapping stars across a surface, unaware that their entire sky is part of a larger room. To detect the hidden direction, we need effects that cannot be explained within the surface alone. Gravity is one possible place to look. High-energy particle collisions are another. Cosmology is another. Particle accelerators, for example, can search for signs that energy has escaped into extra dimensions. If collisions create particles or gravitational effects that move into the bulk, detectors might see missing energy and imbalance, suggesting that something left the brain. This is not simple. Many things in particle physics can create missing energy, including ordinary invisible particles such as neutrinos. So scientists must be extremely careful. The signature of extra dimensions would need to match precise patterns, not just any unexplained gap. So far, no confirmed sign has appeared. Cosmology offers another hunting ground. If extra dimensions influence the early universe, they might leave traces in the distribution of galaxies, the cosmic microwave background, or the behavior of dark matter and dark energy. Again, the evidence is not yet there in a clear way, but the search continues because the universe itself is the largest experiment available. It has been running for billions of years, which is considerate of it, though it does not always label the results clearly. The brain picture also changes how we think about black holes. In some higher dimensional theories, black holes might extend into the bulk or have properties affected by extra dimensions. Tiny black holes, if they could be produced at high energies, might evaporate in distinctive ways. This idea became famous in discussions around powerful particle colliders, though no such tiny black holes have been detected. The point is not that these scenarios are known to happen, but that hidden dimensions would not be quiet decorations. They would affect extreme gravity, high-energy physics, and perhaps the deep structure of space-time itself. There is an interesting tension here. Extra dimensions are proposed because they may explain why our universe looks the way it does. But if they are hidden too well, they become difficult to test. A theory that can never touch observation becomes more like mathematics or philosophy than physics. So the best extra-dimensional models try to do both. They hide the dimension enough to explain why daily life looks ordinary, but not so perfectly that no experiment could ever find a trace. The hidden must be subtle but not completely silent. This balance is delicate. If the extra dimension is too large or affects ordinary matter too strongly, we would already have noticed. Atoms would behave differently. Gravity would not follow the patterns we measure. Stars and planets might not form as they do. If the extra dimension is too small or too weakly connected, it may leave no detectable sign with current technology. Much of the work in this field involves asking what is still allowed. What kind of hidden dimension could exist without contradicting experiments? What new effects would be within reach? Which ideas are ruled out and which remain waiting? Even without proof, brain worlds have changed the imagination of physics. They suggest that the universe we experience could be local in a deeper sense. Not local as in small, but local as in confined to a part of a larger structure. Our entire observable cosmos could be one region, one surface, one extended object in a higher dimensional setting. That is a humbling thought. We used to think Earth was central, then we learned it was a planet around a star. Then we learned the sun was one star in a galaxy. Then we learned our galaxy was one among many. Brain theories raise an even stranger possibility. Perhaps the whole visible universe is only one slice of a larger dimensional reality. There is a quiet pattern in that history. Each expansion of the cosmic picture does not erase what came before. Earth is still home. The sun still rises in our sky because Earth turns. The Milky Way still holds our solar system. The visible universe still contains every galaxy we can observe. But the frame gets larger. The context deepens. A fifth dimension, if it exists in this brain-like way, would be another enlargement of context. It would not make our universe less real. It would make it less alone in the architecture of space. The emotional effect of this idea is unusual. On one hand, it can make us feel very small. Not only are we tiny compared with galaxies, but our entire universe might be a thin surface in a larger space. On the other hand, it can make the ordinary world feel wonderfully rich. The ground beneath you, the air in the room, the quiet pull of gravity, even the simple act of placing a hand on a blanket, all of it may belong to a structure far deeper than it appears. The everyday world becomes the visible skin of a hidden geometry. Gravity in this picture becomes especially poetic without needing to become vague. It is the force that keeps us grounded, but it may also be the force most connected to what lies beyond our brain. It holds us down and hints outward. It makes apples fall and galaxies gather, but it may also whisper of dimensions matter cannot enter. That is a rare combination. The most familiar force may be the one carrying the strangest secret. There is also a practical reminder here. We often think of hidden dimensions as things that would be visible only in exotic places near black holes or at the beginning of time. But if the brain picture is right, the hidden dimension is related to everything. It is not somewhere else. It is part of the deeper setting of every here. Every point in the room could have a relation to the bulk. Every object could be confined to the brain by the same rules. Every gravitational attraction could be shaped, however subtly, by the larger geometry. The hidden is not distant. It is woven into closeness, and yet ordinary life continues. That is one of the remarkable things about deep physics. It can suggest astonishing structures beneath reality while the surface remains calm. You can understand that space-time curves and still make toast. You can know that atoms are mostly empty and still sit comfortably in a chair. You can wonder whether the universe is a brain in a higher dimensional bulk and still feel the simple weight of a blanket over your feet. Scientific wonder does not destroy the familiar. It gives the familiar a longer shadow. So the brain idea leaves us with an image that is both careful and strange. Our universe may be like a vast cosmic sheet, not flat in the simple sense, not small, not unreal, but confined within a higher dimensional structure. Matter and light may move along this sheet, making the world we know. Gravity may reach beyond it, spreading into the bulk and returning to us weakened, perhaps explaining one of the great puzzles of nature. Other brains may exist or may not. Extra dimensions may shape the beginning of the universe or may remain only one possible path in the mathematics of unification. What matters for the story is that the fifth dimension is no longer just a tiny curled loop. It can also be imagined as a hidden direction around a brain, a surrounding space that changes the meaning of where our universe is. This gives physicists a new set of questions. If gravity can move through the bulk, can we detect its leakage? If our brain has shape, does that shape affect cosmic history? If hidden dimensions exist, could they help explain the mysteries that still trouble physics? From the weakness of gravity to dark matter, dark energy, and the search for one deeper theory beneath all forces, those questions bring us naturally to the next part of the journey. Because extra dimensions are not only beautiful ideas about geometry, they're also possible tools for some of the hardest problems in modern science. The fifth dimension, if nature truly uses it, may not simply be an unseen direction. It may be a missing piece in puzzles we've been staring at for decades, a quiet part of the universe that could help explain why the visible world behaves the way it does. Once the brain idea is on the table, the fifth dimension stops being only a strange shape in the imagination. It becomes a possible tool, not a proven answer, not a hidden room with a label on the door, but a way of asking whether some of the hardest problems in physics might look different if we were seeing them from the wrong number of dimensions. That is often how science makes progress. A mystery that seems impossible in one frame may become simpler when the frame changes. The shadow looks tangled, but the object casting it may be ordinary once you turn it around. The universe has given physicists several mysteries that refuse to sit neatly in the picture we already have. Some are cosmic, stretching across galaxies in billions of years. Some are tiny, hiding in the behavior of particles and forces. Some live at the border between what we understand beautifully and what we cannot yet make fit together. The fifth dimension has been suggested in different forms as a possible clue to several of these puzzles. It may explain none of them. It may explain one. It may be a sign that the true answer is even stranger than a hidden direction. But the reason the idea keeps returning is that it offers a new way to think about old problems. The first mystery is gravity itself. Gravity is everywhere, so familiar that we usually notice it only when it becomes inconvenient. It keeps planets in orbit, gathers gas into stars, shapes galaxies, bends light, pulls rain downward, and makes sure dropped toast meets the floor with suspicious commitment to the buttered side. On cosmic scales, gravity is the great architect. Without it, there would be no stars, no planets, no galaxies, no slow gathering of matter into the large structures we see through telescopes. Gravity builds the universe, yet at the level of particles, gravity is shockingly weak. A tiny magnet can lift a paperclip against the pull of the whole Earth. Electromagnetic forces inside atoms are vastly stronger than the gravitational attraction between the same particles. This difference is so extreme that it becomes difficult to ignore. Why should gravity, which rules the cosmos, be so feeble in the small world? Why does it stand apart from the other forces, quietly shaping everything while seeming almost powerless between individual particles? This is often called the hierarchy problem, though the name is much less cozy than the puzzle itself. It asks why the strengths of nature's forces are arranged in such an uneven way, especially why gravity is so weak compared with the forces that govern particles. One possible answer from extra-dimensional theories is that gravity may not be weak in itself. It may only appear weak because it spreads into hidden dimensions. If electromagnetism and the nuclear forces are confined to our brain while gravity can move through a larger bulk, then gravity's influence in our visible universe could be diluted. We would feel only part of it. This idea changes the weakness of gravity into a clue. Maybe gravity is not the odd force that fails to match the others. Maybe it is the only force showing us that our universe is not the whole arena. It is a bit like hearing music faintly through a wall. The sound may not be weak at its source. It may simply be coming from a room you cannot enter. In the same way, gravity may seem faint because some of its presence belongs to a direction beyond ordinary space. Of course, this is not confirmed. If gravity spreads into extra dimensions, there should be ways, at least in principle, to look for the effect. At very small distances, gravity might stop following the usual pattern we expect. It might grow stronger or weaker in a way that suggests more space is available for it to spread through. Experiments have tested gravity at tiny scales, and so far the familiar picture still holds within the limits we can measure. But the search itself is important. It turns the fifth dimension from a dream into something that can be constrained. If the dimension exists, it has less room to hide than it once did. Another mystery is the deep disagreement between general relativity and quantum physics. General relativity describes the large-scale universe with extraordinary success. It gives us curved space-time, black holes, gravitational waves, expanding space, and the bending of light by mass. Quantum physics describes the small-scale universe with equal success. It gives us atoms, particles, fields, uncertainty, and the strange rules behind chemistry, electronics, and light. Each theory works beautifully in its own territory. But when physicists try to combine them fully, trouble begins. This is one of the great unfinished tasks of modern physics. Gravity seems to be geometry. Quantum physics seems to be fields, probabilities, and discrete interactions. At ordinary scales, we can use one theory or the other depending on the problem. But in extreme places such as the heart of a black hole or the first instant of the universe, both should matter at once. There, space-time is intensely curved and quantum effects cannot be ignored. We need a theory of quantum gravity, a deeper framework that can hold both worlds together without breaking. Extra dimensions appear in several attempts to build such a framework. In string theory, for example, the mathematics often requires more dimensions than the familiar ones. These extra dimensions are not added casually. They arise because the theory becomes more consistent when the universe has additional hidden directions. The tiny vibrating strings of the theory need a certain kind of space in which their motions can make sense. If the extra dimensions are curled up into shapes too small to detect, they could remain hidden while still affecting the particles and forces we observe. This does not mean string theory is proven. It remains a major and debated area of theoretical physics, powerful in mathematics and rich in ideas, but not yet confirmed by direct experimental evidence. Still, it shows why extra dimensions are more than decoration. They may be part of the effort to make gravity quantum. They may help replace the sharp conflict between smooth space-time and quantum uncertainty with a deeper structure from which both emerge. If space-time itself is not fundamental, but arises from something beneath it, then hidden dimensions may be part of that deeper layer. The fifth dimension also appears in attempts to understand black holes. Black holes are where gravity becomes almost unbearably strong. There are regions where space-time curves so severely that beyond a certain boundary, nothing can return to the outside universe. General relativity predicts them with confidence, and observations have made them real members of the cosmic landscape. But black holes also raise difficult questions. What happens to information that falls inside? What is the true nature of the singularity, the place where the mathematics of general relativity seems to break down? How does quantum physics behave near the boundary of a black hole? Extra dimensions may change the answers. In higher dimensional theories, black holes can have different shapes and properties. They may stretch along hidden dimensions. They may behave differently at small scales. Some theories even suggested that if gravity becomes stronger at high energies because of extra dimensions, tiny black holes could possibly form in particle collisions. That idea has been tested in searches at powerful accelerators, and no such black holes have been found. But the possibility shows how a hidden dimension could affect the most extreme gravitational objects in the universe. Black holes also lead to another deep idea, that information in a volume of space might be related to information on its boundary. This is often discussed through the holographic principle. The name comes from the idea that a lower dimensional surface can contain the information needed to describe a higher dimensional region. This does not mean the universe is a simple illusion like a projection in a cinema. It means the relationship between dimensions, information, and gravity may be far stranger than ordinary experience suggests. In some versions of theoretical physics, a universe with gravity in one number of dimensions can be mathematically related to a quantum theory without gravity in fewer dimensions. The details are difficult, but the broad lesson is clear. Dimensions may not be as fixed and straightforward as they seem. Then there is dark matter. When astronomers look at galaxies, clusters of galaxies, and the large structure of the universe, they find that visible matter is not enough. Stars and gas move as if extra mass is present. Light bends around galaxy clusters more strongly than visible matter alone can explain. The universe appears to contain a large amount of matter that does not shine, does not absorb light in the usual way, and reveals itself mainly through gravity. This is what we call dark matter. It is one of the great unsolved mysteries of cosmology. Could a fifth dimension explain dark matter? Possibly, though there are many competing ideas. Some extra-dimensional theories predict new particles. These particles might be stable, invisible, and able to interact through gravity, making them possible dark matter candidates. In some models, motion or vibrations in a compact extra dimension can appear to us as heavier particles in ordinary space-time. These are sometimes imagined as a tower of related states, though the mathematics is far more precise than the image. If one of these hidden dimensional particles were stable, it might fill the universe as dark matter. Another possibility is that gravity itself behaves differently because of extra dimensions, and this altered gravity could mimic some dark matter effects. Most evidence still strongly points to some kind of unseen matter rather than only modified gravity, but the question remains open at the edges. The fifth dimension gives physicists another way to ask whether what looks like missing mass might partly be a sign of missing geometry. Again, no proof has appeared, but the connection between dark matter and extra dimensions remains one of the places where the idea is explored. Dark energy is another mystery, even larger and more puzzling. Observations show that the expansion of the universe is speeding up. Something seems to be driving galaxies apart faster over time. The simplest name for this unknown cause is dark energy. It may be a property of space itself. It may be related to vacuum energy. It may be something dynamic that changes over cosmic history. Or it may be telling us that gravity behaves differently on the largest scales. No one knows for certain. Extra dimensions have been suggested here too. If our universe is a brain inside a larger bulk, then the expansion of our brain might be influenced by its relationship to the higher dimensional space. Gravity could behave differently across enormous distances. The shape or tension of the brain could affect cosmic expansion. In some models, what we call dark energy might not be a mysterious substance filling space, but a sign that our visible universe is embedded in a larger geometry. The acceleration of the cosmos might be the shadow of higher dimensional structure. This is a tempting idea because dark energy is so difficult to understand within familiar physics. But it is also very hard to test. The expansion history of the universe can be measured with supernovae, galaxies, cosmic background radiation, and other observations. But many different theories can sometimes produce similar effects. To show that a fifth dimension is responsible would require clear, distinctive predictions. At the moment, dark energy remains dark, not only because it is invisible, but because its explanation is still uncertain. The fifth dimension may also help physicists think about why the laws of nature have the particular values they do. Particles have masses, forces have strengths. The universe has constants that determine how atoms form, how stars burn, and how structures grow. Some of these values seem finely balanced. Change them too much and the universe might not contain stable atoms, long-lived stars, or chemistry complex enough for life. Why are the values what they are? In theories with extra dimensions, the shape and size of the hidden dimensions can influence the properties of particles and forces. This is like the way the shape of an instrument determines its sound. A flute, a drum, and a violin can all vibrate, but each produces different notes because its structure is different. If extra dimensions are compact and shaped in complex ways, their geometry might determine which particles exist and how they interact. The visible laws of physics could be like notes produced by hidden geometry. This is a powerful idea, but also a difficult one. There may be many possible shapes for hidden dimensions, and each shape could produce different low-energy physics. If there are too many possibilities, it becomes hard to explain why our universe chose this particular one. Some physicists connect this to the idea of a landscape of possible universes, where different regions or histories produce different physical laws. This is one of the most controversial and unsettled areas of modern theoretical physics. It may be fruitful, or it may be a sign that the theory is too broad without enough experimental guidance. The fifth dimension opens doors, but not all doors lead to a clear room. Another mystery concerns why we experience three large dimensions of space. If extra dimensions can exist, why are only three large and open to us? Why not two? Why not four? Why would the universe allow exactly the kind of spatial world in which planets, atoms, and living bodies can form as they do? Some explanations are mathematical, some are physical. Some suggest that only three dimensions could expand in the way needed for stable structures. Others suggest that the extra dimensions are compact because of conditions in the early universe. This question sits quietly underneath the whole discussion. A fifth dimension is not only an added feature, it forces us to ask why the visible dimensions have the special status they do. Here, the early universe becomes important. If extra dimensions exist, their size and shape may have been determined very early, perhaps during a phase of rapid expansion or cooling. They may have curled up, stabilized, or become inaccessible as the universe evolved. In that sense, the hidden dimension may be a fossil of the first moments. We do not see it directly, but its structure may have helped set the rules for everything that followed. The universe we experience today could be the result of a much deeper process in which some dimensions grew large while others stayed small. This picture is speculative, but it gives a different feeling to the cosmic past. The early universe was not merely hot and dense. It may have been a place where the shape of reality itself was being settled. Dimensions may have changed their roles. Forces may have separated from a deeper unity. The familiar world may have emerged from a state where space, time, matter, and energy were arranged in ways we can barely imagine. A fifth dimension, if real, may be part of that forgotten architecture. There is also the possibility that extra dimensions explain nothing directly, but still teach us something through their failure. This may sound odd, but it is important. When physicists propose a fifth dimension and then test the consequences, they learn where the idea cannot work. They learn how precisely gravity follows known laws. They learn what particle accelerators do not produce. They learn which cosmic observations fit ordinary models. A wrong idea can still sharpen the right question. In science, even a door that stays closed tells you something about the shape of the hallway. So, could a fifth dimension explain the mysteries we still cannot solve? The honest answer is that it could, but we do not know. It could help explain the weakness of gravity. It could play a role in quantum gravity. It could offer dark matter candidates. It could influence cosmic expansion. It could shape the values of particles and forces. It could help us understand why our universe has the dimensions it does. Or it could be an elegant idea that nature does not use in the way we hoped. The fifth dimension remains one of those possibilities that is too interesting to ignore and too unproven to accept as fact. That tension is part of what makes it such a good subject for quiet thought. It sits between imagination and evidence. It asks us to stretch beyond common sense but not abandon it. It invites us to picture the universe as deeper than it appears, while reminding us that every beautiful picture must answer to measurement. There is something peaceful in that discipline. The universe may be mysterious, but it is not a blur of anything at all. It has patterns. It has constraints. It allows questions, but it does not flatter every answer. Perhaps the fifth dimension is real, curled small at every point, or stretched beyond our brain. Perhaps gravity is the messenger that hints at it. Perhaps dark matter is a particle shaped by it. Perhaps dark energy is a sign of our universe moving through a larger geometry. Or perhaps these mysteries will be solved in completely different ways, and the fifth dimension will remain one of the grand almosts of theoretical physics. Either way, the search changes how we see the world we already have. Because once you have considered the possibility, ordinary space never feels quite as plain. The empty gap between objects becomes a question. The weakness of gravity becomes a clue. The darkness around galaxies becomes a hint that the visible universe is incomplete. The expansion of space becomes not only a cosmic motion, but perhaps a sign of deeper structure. Even if the fifth dimension is never found, It has already done something useful. It has taught us to ask whether reality may be wider than experience and whether the things we call mysteries are sometimes the shadows of dimensions we've not yet learned to see. And that brings us toward the final part of the journey, where the question becomes less about one specific theory and more about what it would mean for the universe to be larger than our senses allow. If the fifth dimension exists, it may not be waiting as a place we can visit, but as part of the hidden grammar of reality itself. It may be written into gravity, into particles, into the early universe, and into the quiet structure of every point around us, present not as a separate world, but as the unseen depth of this one. The question of a hidden fifth dimension brings us to a strange edge of thought. Not the edge of space in the usual sense, not a border where a spaceship could arrive and find a sign saying the universe ends here, please turn around carefully. It is a different kind of edge. It is the edge between what reality may contain and what reality allows us to notice. We are used to thinking that if something exists, then given enough time, enough cleverness, and a sufficiently serious-looking machine, we should be able to see it. But physics has taught us again and again that existence and visibility are not the same thing. Some parts of nature are not absent, they are simply hidden by scale, by distance, by weakness, by geometry, or by the limits of the creatures asking the question. That is why the fifth dimension remains so interesting. It is not only a proposal about extra space, it is a reminder that our universe may be larger than our experience of it. The familiar world may be true without being complete. Your room is real. Your body is real. The stars are real. The planets, atoms, fields, and galaxies are real. But they may belong to a structure whose full shape is not directly available to human senses. In the same way that a shadow is real but not the whole object, the visible universe may be a real surface, slice, or low-energy expression of something deeper. This is a difficult idea because our senses make reality feel finished. When you look around, space seems to be all there. It has distance, it has direction, it has surfaces, walls, roads, skies, and horizons. If you walk across a room, you arrive at the other side. If you climb a hill, you reach the top. If you look at the night sky, you see depth stretching away in every direction. The three dimensions of space do not feel like a partial view, they feel like the whole map. That feeling is powerful, but it is not proof. It is only the experience of a body built to survive in three large spatial dimensions. A fish does not need to understand the atmosphere to swim. A bird does not need to understand radio waves to fly. A person does not need to sense curved space-time to walk down a street. Life uses the parts of reality that matter most for living. Evolution gave us practical senses, not complete cosmic instruments. We can detect light, sound, touch, taste, and smell within ranges useful for bodies like ours. We can judge the shape of a room, the distance to a tree, the warmth of a fire, the voice of a friend. But nature contains far more than these senses report. We built science partly because our bodies could not tell the full story on their own. The hidden fifth dimension, if it exists, would belong to that larger story. It may be curled up at every point in space, too small for ordinary objects to enter. It may be a direction into a higher dimensional bulk, while our matter remains confined to a brain. It may be part of a mathematical structure that helps describe forces or particles without being accessible as a place. Or it may not exist at all. The honest answer is still unknown. But the possibility matters because it challenges the assumption that reality must match what our senses can comfortably picture. This is one of the quiet lessons of modern physics. The universe is not always arranged for human imagination. Quantum particles do not behave like tiny marbles. Time does not flow at the same rate for everyone. Gravity is not just a pull, but the curvature of space-time. Empty space is not truly empty in the simple sense. The expansion of the universe is not an explosion into ordinary space, but the stretching of space itself. Each idea asks the mind to let go of a familiar picture and accept a deeper one. A fifth dimension asks for the same patience. If the universe is larger than our senses allow, then the word larger needs care. We are not necessarily speaking of more distance in the ordinary sense. A fifth dimension might not make the universe larger the way adding another country makes a map larger. It might make the universe larger in structure. It might mean that every point in space has hidden depth. It might mean that what appears to us as a simple location is actually connected to a small, compact geometry. It might mean that our entire observable cosmos is embedded in something with more directions than we can move through. This kind of largeness is not measured only by miles or light years. It is measured by degrees of freedom, by geometry, by what can exist beyond ordinary motion. Think again of the flat creatures on a surface. Their universe may be enormous in the directions they know. They could have flat galaxies, flat oceans, flat cities, flat astronomers, and flat evening routines involving flat cups of tea. Though drinking them may raise serious engineering problems, to them their world could seem vast beyond imagination. Yet from a three-dimensional view, it would still be only a surface. Its size within the surface would not reveal the room around it. In the same way, our universe may be vast in the directions we know and still not exhaust the full structure of space. This does not mean we should imagine ourselves as trapped or deceived. The universe we experience is not fake because it might be incomplete. A map is not fake because it leaves out the smell of rain or the sound of traffic. A photograph is not fake because it shows one angle. A slice of bread is not fake because it is not the whole loaf. A point worth remembering if you happen to be hungry during a science video. Our visible universe may be a valid part of reality even if a higher dimensional view would reveal more. The real question is whether the hidden part has effects. Physics does not simply ask whether we can imagine more dimensions. It asks whether more dimensions help explain the world we measure. Could gravity be weak because it spreads beyond our brain? Could dark matter be related to particles shaped by hidden geometry? Could dark energy reflect the behavior of our universe inside a larger bulk? Could the values of particle masses and forces come from the shape of compact dimensions? Could quantum gravity require more structure than four-dimensional space-time? These are serious questions, but not settled ones. That uncertainty is important. A fifth dimension is not a confirmed fact. It is a possibility explored because it appears naturally in some theories and because it may help with real puzzles. The search for it has not produced decisive evidence. Experiments have not found clear signs of gravity changing because of extra dimensions at small distances. Particle accelerators have not revealed unmistakable missing energy patterns or new states that prove hidden dimensions. Observations of the cosmos have not yet forced us to accept a higher dimensional universe. The fifth dimension remains hidden in the strongest sense. It is still not known whether it is physically there, but an unconfirmed idea can still be valuable when it is disciplined by evidence. It can guide experiments, it can sharpen questions, it can show what kinds of universes are possible and which are ruled out. It can reveal connections between geometry, particles, and gravity that might otherwise remain unnoticed. Sometimes science advances by discovering that an idea is right. Sometimes it advances by discovering exactly how and where an idea is wrong. Both outcomes teach us something. There is a calm honesty in this. Physics is not a collection of dramatic claims. It is a conversation with nature, and nature answers slowly. We ask through mathematics, telescopes, detectors, clocks, particle collisions, and careful measurements of gravity. Nature answers through patterns, numbers, limits, and sometimes silence. When it comes to the fifth dimension, the answer so far is not a clear yes. It is also not a final no. It is more like a quiet door at the end of a hallway with light under it. Perhaps, or perhaps only our own curiosity reflected back at us. One reason the idea continues to attract attention is that it fits a larger pattern in the history of science. Again and again, the universe has turned out to be wider than the human view. Earth was once treated as the center of everything. Then it became a planet. The sun was once treated as special in a small sky. Then it became one star among many. The Milky Way was once treated as the whole universe. Then it became one galaxy among countless others. Matter was once treated as solid and continuous. Then it became atoms, particles, fields, and probabilities. Space was once treated as a passive container. Then it became dynamic space-time. A fifth dimension would be another widening of the frame, but the pattern does not guarantee the result. We should not say because science has found hidden things before, this hidden thing must exist. That would be too easy. The universe may be deeper in some ways and simpler in others. It may contain extra dimensions, or it may achieve its mysteries without them. The fifth dimension is not inevitable. It is possible, and possible is enough to keep the question alive when the mathematics is serious and the puzzles remain unsolved. There is another reason the idea feels compelling. It turns geometry into explanation. We're used to thinking of geometry as something learned in classrooms with lines, surfaces, angles, and shapes. But in modern physics, geometry can be physical. The geometry of space-time is gravity. The geometry of hidden dimensions, if they exist, could shape forces and particles. This means that the deep laws of nature might not be separate instructions written on top of the universe. They might be consequences of the universe's shape. The rules may come from the structure itself. That is a powerful way to think. A planet follows a curved path because space-time is curved. A particle may have certain properties because hidden dimensions allow only certain patterns. A force may appear in our world because geometry in a larger world casts a shadow into ours. The fifth dimension in this view is not an extra detail. It is a possible part of the machinery that makes the visible laws what they are. If true, the universe would be larger not only in extent but in explanation. Still, even if the fifth dimension exists, we may never experience it the way we experience ordinary space. We may not travel through it. We may not see it. We may not build a door into it. It may be too small, too inaccessible, or too deeply tied to the structure of fields and gravity. This can feel disappointing at first because the imagination wants a grand entrance. It wants a hidden corridor, a shimmering boundary, a way to step sideways out of the world. But physics is often quieter than that. The hidden dimension may not be a place to visit. It may be a reason things are as they are. That thought can be more interesting than the fantasy. A visitable fifth dimension would be thrilling, certainly, and perhaps inconvenient for map makers. But a fifth dimension that silently shapes gravity, particle behavior, or cosmic history would be profound in a different way. It would mean that every ordinary event is connected to deeper structure. The fall of a stone, the orbit of a planet, the glow of a star, the charge of an electron, the expansion of the universe, all might carry traces of a hidden geometry. The fifth dimension would not be elsewhere. It would be part of the hidden meaning of here. This changes the feeling of the visible world. The room around you is still familiar, but it becomes less plain. The distance between the wall and the window is ordinary distance, but perhaps space at each point has hidden structure. Gravity holding you gently to Earth is ordinary gravity, but perhaps it is also the one force that reaches beyond our brain. The night sky is ordinary darkness between stars, but perhaps the motion of galaxies is influenced by matter, energy, or geometry not fully visible. The familiar world becomes a surface with depth, a sentence with grammar beneath it. There is a peaceful humility in accepting that human beings occupy a tiny part of the universe, not only in size, but perhaps in access. We live in a narrow band of temperatures, pressures, speeds, energies, and perceptions. We know the world through instruments made from the world, and yet, from within these limits, we have learned astonishing things. We have measured the age of stars, detected waves in space-time, mapped the afterglow of the early universe, split atoms, built quantum devices, and sent machines beyond the planets. We may be limited, but we are not helpless. Our senses are small, but our reasoning can reach far. The fifth dimension is a perfect example of that reach. No one has seen it. No one can point to it. No one can draw it accurately as a spatial direction beyond the ones we know. Yet by using mathematics, analogy, and experiment, physicists can ask whether it might exist. They can work out what it would imply. They can compare those implications with measurements. They can narrow the possibilities. That is one of the great achievements of science. It lets creatures with three-dimensional bodies ask questions about spaces they cannot imagine. And perhaps that is why the idea belongs so well in a quiet night of thought. It is not only about physics. It is about the relationship between reality and perception. What we see is not all that is. What we can picture is not all that can be described. What feels obvious may be only the nearest layer. The universe may be larger than our senses allow because reality is not built around our convenience. It is built according to deeper rules, and our task is to listen carefully enough to hear them. If a fifth dimension is ever confirmed, it would be one of the great changes in human understanding. It would mean that the structure of the universe includes a hidden direction beyond space-time as commonly experienced. It would reshape our view of gravity, particles, cosmology, and perhaps the origin of the laws themselves. It would not make everyday life collapse into strangeness. Tea would still cool. Beds would still be comfortable. Alarms would still arrive too early with their usual confidence. But beneath those ordinary facts, we would know that space has a secret depth. If it is never confirmed, the journey will still have mattered. The search will have sharpened our understanding of gravity and quantum theory. It will have tested the limits of hidden geometry. It will have reminded us that not every beautiful idea becomes a fact, and that this is not a weakness of science but one of its strengths. Science does not protect ideas because they are beautiful. It tests them because truth matters more than elegance. The fifth dimension may be real, or it may be one of the universe's most graceful unanswered invitations. For now, we remain in the world we know. 3 large dimensions of space, 1 dimension of time, a universe expanding, curving, cooling, forming stars, making planets, and eventually producing minds that lie awake wondering whether space has a hidden side. That alone is remarkable. The universe may or may not contain a 5th dimension, but it certainly contains the ability to question itself through us. Atoms formed in stars have become beings who ask whether the geometry of reality is complete. There is something quietly wonderful about that, even without adding another direction. So as this thought settles, return gently to the space around you. Notice the room again, the ceiling above, the floor below, the quiet distances between things. This is the space your body knows. It is dependable, useful, and real, but perhaps it is also only the surface of a deeper order. Perhaps the universe is folded, layered, or extended in ways we have not yet proven. Perhaps gravity is whispering through a hidden direction. Perhaps the laws of physics are shaped by geometry too small or too inaccessible for our senses. Or perhaps the mystery will lead somewhere else entirely. Either way, the question has changed the room. Space is no longer just emptiness. It is a possibility, a structure, a question still open at the edges. And if sleep is beginning to arrive, you can let the mystery remain unfinished. Physics does not require every answer before morning. Some questions are patient. They can wait in the dark, calm and enormous. While the visible world grows quiet around you,